Tonight, we are traveling back to a moment when Earth almost lost its warmth forever. A moment when the line between living oceans and endless ice may have been thinner than anyone once imagined. A planet on the edge of permanent ice. Earth has frozen before, but not every frozen world ever recovers. Scientists know that once ice spreads far enough, it begins to protect itself, reflecting sunlight away and cooling the planet even more. Early Earth faced this danger under a weaker sun, receiving far less energy than it does today. By simple physics, liquid oceans should not have survived. And yet, geological evidence shows that water remained, flowing and persistent, even as conditions pushed the planet toward global freeze. Ice does not arrive gently. As it advances, cooling accelerates, and recovery grows harder with every step. Studies suggest that a fully frozen planet does not wait patiently to warm again. Without very specific conditions, it stays frozen, not for ages but for geological eternity. If Earth had crossed that line, there would be no forests, no animals, no humans. But how close did Earth come to freezing forever? What stopped the planet from crossing that final threshold? How fragile was the balance that kept oceans liquid? And if Earth almost failed once, why has it not failed again? Tonight, we will gently follow the traces of a world that nearly became silent ice. But before we begin, if you find comfort in these quiet journeys through science and story, it would mean the world to me if you gave this video a gentle like and maybe tapped subscribe. It helps more curious minds like you find their way to this peaceful little corner of the internet and lets the algorithm know that sleep and science belong together. And if you'd be so kind, let me know in the comments where you're winding down from tonight and what time is it there. I love seeing how far across the world these soft explorations travel. Remember, as you listen, that without this frozen chapter, there may never have been us at all. Now take a deep breath, let your shoulders loosen, close your eyes, and together let us step softly toward the moment Earth almost stopped being warm. In the earliest moments after Earth took shape, the planet did not resemble a world that could cradle water or life. It was a surface still learning how to exist, glowing in places, restless everywhere. Heat rose not only from the young sun above, but from within the planet itself, where gravity had compressed matter so tightly that stone behaved more like a slow glowing fluid than solid ground. The sky was not yet a sky in the familiar sense. Gases escaped from the interior in steady breaths, mixing with the remnants of material left over from formation. The air shifted constantly, thick in some places, thin in others, shaped by forces that had not yet settled into balance. Nothing held still for long. Energy moved freely, colliding, scattering, rearranging. Across the surface, impacts arrived without warning. Fragments of rock and metal crossed the inner solar system, drawn inward by gravity, striking Earth again and again. Each collision delivered new material, but also released enormous heat. The ground melted locally, then flowed, then cooled again, only to be shattered by the next arrival. This was not destruction layered on creation. It was creation itself, chaotic and unfinished. Much of the surface remained molten or close to it. Vast regions glowed faintly in the dark, rivers of magma creeping beneath a fragile crust that cracked and reformed repeatedly. Where the surface did cool, it did so unevenly, creating islands of solidity surrounded by seas of heat. There were no stable land masses yet, no continents with edges or interiors, only temporary patches of cooling rock drifting atop a restless interior. Without continents, the planet had no familiar boundaries. There were no coastlines, no shelves, no long stretches of land to interrupt the flow of heat between interior and surface. everything connected directly to everything else. Energy moved upward, outward, and away, unchecked by structure. The planet was learning how to lose heat, and it was learning slowly. Above this shifting ground, the atmosphere thickened as volcanic gases accumulated. Carbon compounds, water vapor, and other molecules poured out of fissures and vents, carried upward by heat. The air trapped warmth efficiently, yet it was unstable, constantly rearranged by temperature differences and impacts from above. Clouds formed and vanished. Pressure changed. The surface existed beneath a ceiling that never fully settled. And still, water began to appear. At first, it arrived invisibly, carried as vapor in the thick air. Each cooling moment allowed some of it to linger a little longer before returning to the sky. As impacts slowly decreased and the surface cooled just enough, rain began to fall. Not gentle rain, but relentless sheets of it, falling onto hot rock, hissing and flashing back into vapor, then falling again. Over time, the balance shifted. Cooling outpaced reheating in certain regions. Water pooled briefly, then longer, collecting in low places created by the uneven crust. These early oceans were not blue or calm. They were dark, steaming, and acidic, absorbing minerals from the rock beneath them. Heat rose through them from below, while cold seeped in from above. They were born into conflict. The presence of liquid water did not mean safety or stability. The planet hovered near thresholds that shifted constantly. A little more heat, and oceans would vanish back into the air. A little less, and ice would begin to creep across the surface, reflecting sunlight and reinforcing cold. In this early climate, small changes carried enormous weight. Without continents to regulate weathering, without established cycles to balance gases, Earth relied on raw physics to find its footing. Heat escaped where it could. Gases accumulated until they altered the balance again. Water moved between sky and surface in vast, slow rhythms. The planet was not designed for comfort. It was negotiating survival through motion. What emerged from this hostile beginning was not order, but persistence. The surface cooled enough to remain solid in places. Water endured long enough to deepen and spread. The atmosphere thickened into something capable of holding warmth without boiling oceans away. None of this was guaranteed. Each step depended on timing, on rates that happened to align closely enough to prevent collapse in either direction. This early climate did not offer refuge or predictability. It offered narrow margins and constant adjustment. Earth remained a world in flux, suspended between extremes, shaped by forces still finding equilibrium. In this restless balance, the foundations of everything that followed were laid quietly, without intention, guided only by the slow patience of physical law. As Earth slowly learned how to hold water and release heat without tearing itself apart, another presence shaped its fate from far away. The sun, steady and distant, was not yet the star we know today. It shone with patience, not power. Burning more softly in its youth, its light stretched thinner across space. This gentle output mattered deeply because everything unfolding on Earth depended on the balance between warmth arriving from above and heat escaping into the dark. In those early ages, the sun delivered noticeably less energy than it does now. The difference was not dramatic in appearance, but it was profound in consequence. A planet placed at Earth's distance, receiving that reduced light, should have struggled to keep liquid water at its surface. Physics alone suggested a colder world, one where oceans would stiffen into ice and remain there, locked beneath a pale sky. This expectation did not come from imagination. It emerged from the simplest descriptions of how planets exchange energy with space. Incoming sunlight warms the surface. Reflected light escapes. Heat radiates outward. When these flows are tallied, early Earth appears to fall short. The numbers lean toward ice, toward a world unable to sustain open seas for long. In these calculations, the planet cools quickly, the surface brightens with frozen reflection, and the chill deepens. Yet the rocks tell a different story. Long before continents settled into familiar shapes, long before life reshaped the atmosphere, liquid water left its mark. Minerals formed only in the presence of flowing water appear in Earth's oldest surviving crust. Chemical signatures point to oceans that endured, not briefly, but persistently. These traces do not align with a world locked in ice. They speak quietly of rainfall, of circulation, of warmth sufficient to keep water moving. The contradiction rests here, calm but unyielding. A faint young sun should have frozen the planet. The geological record insists that it did not. This tension became one of the most enduring puzzles in Earth science, not because it was loud or dramatic, but because it sat at the foundation of everything that followed. If the early sun could not provide enough heat, then something else must have compensated. Some combination of atmospheric trapping, surface conditions, or internal energy had to bridge the gap, gently but consistently, over spans of time too long for chance alone. The difficulty lies in how narrow that bridge appears to be. A small reduction in warmth would have allowed ice to spread. As ice advanced, it would have reflected more sunlight back into space, amplifying the cooling. The planet would slip further toward cold with each reflective surface added. Once this process gained momentum, recovery would become increasingly difficult, requiring forces strong enough to overwhelm a self reinforcing freeze. Simple models capture this slide easily. They show a planet tipping into ice with little resistance. They show sunlight weakened, oceans sealing, and the surface settling into a stable frozen state. These outcomes are not extreme. They are natural results of basic physical relationships. That they did not occur on Earth is what makes the problem persistent. The sun itself was changing, brightening slowly as nuclear processes deepened at its core. But this increase unfolded over immense time, far too slow to rescue a planet that froze early and thoroughly. If Earth had crossed the icy threshold during those early ages, the sun would not have reversed it quickly. The world would remain cold long enough for surface conditions to become permanently altered, and yet water flowed. This means that Earth's climate system found a way to remain warm enough despite reduced solar input. Not warm in a comfortable sense, but warm enough to avoid collapse. The mechanisms responsible did not announce themselves clearly. They left indirect traces, subtle balances written into stone, and chemistry rather than obvious markers. What makes this contradiction central is not simply that it exists, but that it persists across different lines of evidence. No single adjustment resolves it fully. Each proposed explanation helps, but none alone removes the tension. The story becomes one of overlapping influences, each nudging the planet just far enough from the edge. In this light, early Earth appears not as a stable world, but as one constantly negotiating with its star, heat arriving just slowly enough, trapping mechanisms responding just strongly enough, losses balanced by gains without a wide margin for error. The sun, faint but patient, provided a backdrop against which every other climate process had to work harder. This quiet imbalance does not dominate the scene. It hums beneath it, steady and unresolved, shaping the direction of every chapter that follows. Earth's early warmth was not guaranteed by its position alone. It was earned through a delicate interplay between star, surface, and sky, an interplay that remained vulnerable long after the oceans first appeared. As Earth balanced beneath a gentler sun, its climate remained sensitive to small shifts. Heat arrived slowly, and whatever escaped was not easily replaced. In such a world, the behavior of the surface mattered as much as the warmth falling from above. Among all surfaces a planet can wear, None alters fate as quietly and powerfully as ice. When rock or water lies exposed, sunlight is absorbed and transformed into warmth. Energy sinks inward, lingering long enough to soften edges and sustain motion. Ice behaves differently. Its pale surface turns light away, sending much of the sun's gift back into space before it can do its work. What might have warmed the planet instead vanishes, reflected upward, lost to the dark. This single property changes everything. Cooling becomes self-reinforcing. As temperatures fall, ice begins to form in small patches, along high ground or in long shadows where warmth struggles to linger. Each new patch brightens the surface slightly. Each brightened surface reflects a little more sunlight. With less energy absorbed, temperatures fall further. The process feeds itself quietly, without drama, step by step. On a world already short of heat, this feedback gains strength quickly. Ice spreads not because it is aggressive, but because it is efficient. It requires no storm or catastrophe, only time and a gentle imbalance. What begins as seasonal frost can harden into permanence. What forms at the poles can creep outward, slow and persistent, following lines of latitude like a closing hand. As ice advances, it alters more than temperature. Winds change as temperature gradients sharpen. Clouds reorganize. Moisture becomes trapped in frozen form, reducing the movement of water through air and land. The planet's surface grows simpler, smoother, more uniform. Diversity of terrain gives way to broad, reflective plains. Recovery from this state is difficult, not because warmth cannot return, but because ice resists it. To reverse the spread, the planet must absorb more energy than before, enough not only to halt cooling but to melt what has already formed. This requires a stronger push than the one that initiated freezing. The system becomes asymmetric, easy to tip into ice, hard to pull back out. Once ice reaches lower latitudes, the challenge deepens. Sunlight strikes these regions more directly, yet the reflective surface rejects it. Even under a brighter sky, ice can persist, holding its ground against incoming warmth. The planet becomes locked into a state where the usual balance between day and season no longer applies. At this stage, the climate no longer responds gently to change. Small increases in warmth may do little. Large increases may be required to make a visible difference. The system settles into a new stability, colder and brighter than before, protected by its own reflection. This is not a temporary winter. It is a structural shift. In planetary terms, this feedback loop is one of the most dangerous paths a world can follow. It does not rely on rare events or sudden disasters. It arises naturally from the way ice interacts with light. Any planet with water, a reflective surface, and limited incoming energy carries this risk within it. Earth felt this danger keenly in its early history. With a faint sun overhead and a climate still assembling its defenses, the spread of ice represented more than cold weather. It threatened to silence the processes that allowed oceans to exist at all. Once sealed beneath ice, water could no longer exchange heat with air. Circulation would slow, gases would become trapped. The surface would grow still. What makes this feedback so powerful is its patience. It does not rush. It waits for conditions to align, then proceeds without interruption. There is no natural stopping point until either ice dominates the surface or sufficient warmth breaks the cycle. In between, there is little room for balance. This is why planets that enter deep freeze often remain there for extraordinary lengths of time. Without a strong internal source of heat or a dramatic change in incoming energy, ice holds its territory. The world becomes stable in its cold, secure in its reflection, resistant to recovery. Earth's survival required avoiding this trap not once, but repeatedly. Each time temperatures fell, the planet approached a familiar slope. Each time ice formed, it carried with it the quiet risk of acceleration. That this did not culminate in permanent freeze speaks not to the weakness of the process, but to the presence of other forces working just strongly enough to counter it. In the soft light of deep time, ice stands revealed not as a passive outcome of cold, but as an active agent shaping planetary destiny. Its brilliance hides its danger, its silence conceals its power, and in Earth's early climate, it remained a constant companion, waiting for the moment when reflection might outweigh warmth and balance might finally slip. As ice began to reveal its quiet authority over climate, a deeper distinction emerged, one that separates temporary hardship from lasting transformation. Not all cold worlds are the same. Some pass through ice ages and return, others cross a boundary and never come back. Understanding this difference reshapes how planetary survival is measured. An ice age is a period of imbalance, not a final state. Ice advances and retreats, responding to shifts in sunlight, atmospheric composition, or orbital rhythm. Even at its height, large regions of the planet remain exposed. Dark oceans absorb heat. Winds and currents continue to move energy across the surface. Beneath the ice, systems remain active, waiting for conditions to soften. A full planetary freeze is something else entirely. In this state, ice dominates nearly every latitude. Oceans seal beneath thick layers, cutting off their ability to exchange heat with the air. The surface brightens until most incoming sunlight is reflected away. The planet no longer breathes in warmth efficiently. What little heat arrives struggles to penetrate the frozen shell. Once this condition takes hold, the climate stops behaving like a flexible system and begins to resemble a locked structure. Change slows, feedbacks weaken. The surface settles into long stillness. Without exposed water or rock to absorb sunlight, warming forces lose their leverage. The planet enters a deep equilibrium that resists disruption. Recovery from such a state requires more than patience. It demands a powerful and sustained source of energy. Internal heat alone is rarely enough. Radioactive decay warms interiors slowly and gently, insufficient to melt global ice from below. External warmth must increase dramatically, or atmospheric trapping must intensify far beyond ordinary ranges. This is why some planets never recover once frozen. Their stars do not brighten fast enough. Their atmospheres thin rather than thicken. Their internal activity declines. Each supporting process weakens over time, not strengthens. The cold becomes self-maintaining. Mars offers a quiet illustration. Long ago, it held liquid water at its surface. Valleys carved by flowing streams remain etched into its crust. Yet, as the planet cooled and its atmosphere thinned, ice gained control. With less gravity to hold gases and less internal heat to drive renewal, Mars slipped into a frozen state that persists today. Its ice does not retreat. It rests beneath a pale sky, stable and enduring. Beyond Mars, icy moons provide another view. Worlds like Europa and Enceladus remain frozen at the surface despite internal warmth below. Thick ice shells isolate subsurface oceans from sunlight. These oceans may persist for immense spans of time, yet the surface remains locked in cold. From above, these worlds appear static, bright, and unchanging. In each case, ice acts as insulation and barrier at once. It traps heat beneath, while preventing warmth from reaching the surface. It preserves interior motion while enforcing exterior stillness. The planet becomes divided, active within, frozen without. When scientists speak of permanent freeze, they do not mean absolute stillness or the absence of all energy. They mean a state where surface conditions remain frozen for geological spans so long that reversal becomes improbable. Millions of years stretch into hundreds of millions. Change slows until it blends into the background of time. In this context, the word forever is not poetic exaggeration. It reflects the scale at which planetary systems operate. Without a clear mechanism for recovery, frozen states persist longer than continents last, longer than atmospheres remain intact, longer than stars remain unchanged. For a surface world, this might as well be eternity. Earth stood uncomfortably close to this boundary more than once. The difference between an ice age and a permanent freeze lay not in temperature alone, but in structure. As long as open water survived somewhere, as long as dark surfaces absorbed sunlight and exchanged heat, the planet retained flexibility. Once those anchors disappeared, recovery would demand extraordinary intervention. What makes this distinction unsettling is how subtle the crossing can be. The shift from temporary ice to permanent lock does not require dramatic catastrophe. It requires only persistence. Ice must spread far enough and remain long enough for feedbacks to harden into structure. In the slow rhythm of planetary time, permanence often arrives quietly. It settles in when opposing forces weaken just enough to stop pushing back. From that moment forward, the world no longer oscillates. It rests. Earth's story continues because it avoided this rest, not because the danger was small, but because the balance held. The meaning of a permanent ice planet lies in what did not happen and in how easily it might have. As the planet continued its careful balancing act, water did more than merely appear and vanish. It endured, not as mist alone, not as brief floods that flashed away, but as oceans that settled into the low places of a restless world. Their presence is not inferred from imagination or hope. It is recorded quietly in stone. Within Earth's oldest surviving rocks, there are minerals that carry a specific memory. Their crystal structures only assemble when water is present for long periods, moving slowly, interacting gently with rock. These minerals do not form in steam or in brief contact with moisture. They require stability. They require liquid water, lingering long enough to reshape chemistry grain by grain. Some of these minerals hold ratios of atoms that reveal the temperatures at which they formed. Others trap tiny inclusions, microscopic pockets that once contained ancient water itself. Together, they speak of environments where water flowed, pooled, and circulated beneath skies that did not instantly freeze it solid. The temperatures implied by these records are modest, not warm in a modern sense, not tropical or gentle, but safely above freezing, warm enough for water to remain liquid across seasons, warm enough for rain to fall and return again, warm enough for oceans to deepen rather than vanish. This is where the tension sharpens. Earlier forces had already stacked the odds against such conditions. The sun's light was faint. Ice, once formed, would have reflected precious energy away. The surface lacked continents to stabilize cycles, yet water persisted anyway, quietly contradicting expectation. To keep oceans liquid, the planet needed a narrow range of temperatures. Too cold, and ice would spread relentlessly. Too warm, and water would escape into the air, vulnerable to loss. The early oceans existed between these extremes, held there by a balance that appears improbably precise. The stones do not suggest brief windows of warmth followed by long freezes. Instead, they imply continuity. Water was present again and again across different regions and times. This persistence demands explanation because it should not have been easy to maintain. Basic physics offers little comfort here. With reduced sunlight, even small losses of heat could have tipped the system. Ice should have crept outward, reflection should have amplified cooling, the planet should have slid toward stillness. And yet, the oceans remained open. What this implies is not a single miraculous solution, but a layering of effects. The atmosphere must have held on to heat more effectively than simple models allow. Gases released from within the planet likely lingered longer, thickening the sky and slowing the escape of warmth. Water vapor itself, abundant above the oceans, would have added to this gentle trapping. Clouds may have played a role as well, sometimes reflecting sunlight away, sometimes holding heat close, depending on their height and thickness. In a world without modern weather patterns, these clouds behave differently, their balance delicate and shifting. Heat from below also mattered. The young planet retained more internal energy than it does now. Warmth rose steadily through the crust, leaking into the oceans from beneath. This was not enough to dominate the climate, but it added another quiet contribution, lifting temperatures just slightly, just persistently. Each of these influences alone would have been insufficient. Together, they formed a fragile network of support. Remove one strand, and the system might have failed. Strengthen one too much, and overheating could follow. The early oceans existed within this narrow corridor, protected not by certainty, but by convergence. This is why the temperature problem remains central. The evidence for liquid water is strong, yet the conditions required for it appear finely tuned. The planet was not safely warm. It was narrowly warm enough. In this light, the first oceans appear less like an inevitable outcome and more like a sustained effort by the planet itself. Not conscious or directed, but governed by the slow interplay of physical laws that happen to align. Water flowed not because conditions were ideal, but because they were just sufficient. The surface above these oceans remained harsh. Storms likely raged, impacts still occurred, chemistry was aggressive. Yet beneath it all, water persisted, absorbing heat, moving it across the globe, softening extremes. The oceans became reservoirs of stability in an otherwise volatile world. Their existence changed everything that followed. Water moderated temperature. It dissolved gases. It interacted with rock. It became a partner in climate, not merely a passenger. But at this stage, nothing guaranteed its survival. The balance could still slip. The first oceans did not prove that Earth was safe. They proved only that, against expectation, it was not yet lost. As the oceans settled into their uneasy balance, another layer of protection gathered above them. The early atmosphere was not shaped by forests or plankton or breathing creatures. It belonged entirely to the planet itself, assembled from gases released by stone, heat, and pressure. This sky was thick, reactive, and unfamiliar, yet it played a quiet role in keeping the surface from slipping into permanent cold. Volcanoes and fissures released vast amounts of gas from Earth's interior. Carbon compounds rose steadily, accumulating in the air because there was nothing yet to remove them efficiently. No soils rich with roots, no shells sinking to the seafloor, no biological pumps drawing carbon downward. What entered the atmosphere tended to stay there, lingering and building over time. Carbon dioxide, in particular, reached levels far beyond anything known in later ages. It spread through the sky like a slow blanket, invisible but effective. When sunlight reached the surface and warmed rock and water, That warmth did not escape easily. It was absorbed and re-emitted, then caught again, gently delayed on its journey back into space. This did not create heat from nothing, it simply slowed the loss, buying the planet time. Alongside carbon dioxide, another gas drifted upward from the young world. Methane emerged from chemical reactions deep within the Earth and from interactions between water and rock at the seafloor. In an atmosphere untouched by oxygen, methane survived far longer than it would today. It accumulated quietly, adding its own influence to the balance of warmth. Methane is light and subtle, but its ability to trap heat is strong. Even small amounts can alter temperature when conditions are right. In the early sky, its presence mattered more than its quantity. It joined carbon dioxide in shaping an atmosphere that behaved very differently from the one we know. This greenhouse effect did not resemble a controlled system. It fluctuated. Gas levels rose and fell with volcanic activity, impacts, and the slow cooling of the planet's interior. The atmosphere thickened, then thinned, always adjusting. Yet through these changes, one pattern held. Heat escaped more slowly than it otherwise would have. What makes this period remarkable is that all of this occurred without life's guidance. There were no leaves adjusting gas exchange, no algae regulating chemistry, no feedbacks driven by ecosystems. The planet relied solely on physical and chemical processes. Rock breathed, water reacted, heat moved upward, the sky responded. This created a form of climate regulation that was crude but effective. As temperatures cooled, volcanic activity continued to release carbon dioxide, strengthening the atmosphere's ability to retain warmth. As temperatures warmed, chemical reactions between rainwater and rock slowly removed some carbon from the air, though this process worked gently and over long spans. The balance was slow, but it leaned towards stability. Methane added a delicate layer to this arrangement. In the absence of oxygen, it persisted, enhancing warming during periods when carbon dioxide alone might not have been enough. Its presence likely fluctuated, rising during certain chemical conditions and falling when sunlight broke it apart high in the atmosphere. Each rise and fall nudged the climate slightly, never dominating, always contributing. The early greenhouse effect did not create a warm paradise. It created survivable margins. Oceans remained liquid but cool. Ice formed at the edges but did not overwhelm the surface. The planet hovered near thresholds, supported by gases that quietly altered the flow of energy. This balance was not guaranteed to last. If volcanic output had slowed too much, gases would thin and cooling would deepen. If chemical removal had accelerated, warmth would fade. The atmosphere existed in a narrow window, shaped by competing processes that happened to counter one another just enough. In this sky, heat was not generated by life, but preserved by chemistry. The absence of oxygen allowed methane to linger. The absence of biology allowed carbon dioxide to accumulate. The planet used what it had, and what it had was stone, water, and time. The greenhouse gases of this era were not signs of excess. They were signs of necessity. Without them, the faint sun above and the reflective ice below would have pushed Earth toward stillness. With them, the planet retained motion, circulation, and open water. This phase of Earth's history reveals a quiet truth. Long before life shaped the climate shaped the possibility of life. The early atmosphere did not know what it was protecting. It simply followed the rules of chemistry and physics, holding warmth close long enough for the story to continue. As gases gathered in the sky and oceans settled into their narrow range of survival, another process worked patiently beneath the surface. It did not announce itself with constant violence, but it never fully rested. Deep within the planet, heat continued to move, carrying carbon upward from the interior in a slow, persistent exchange between rock and sky. Volcanoes became the quiet messengers of this movement. Early Earth held far more internal heat than it does now. The planet was young, its interior still warm from formation and compression. This heat softened rock at depth, allowing it to move, melt, and rise. Where fractures opened in the crust, molten material escaped, releasing not only lava but gases trapped within the planet since its earliest assembly. Among these gases, carbon dioxide played a central role. Locked deep within minerals, carbon was carried upward and released into the atmosphere through volcanic breath. This process did not depend on climate, sunlight, or surface conditions. It was driven by internal heat alone. As long as the planet remained warm inside, carbon continued to emerge. This steady release mattered because it operated on timescales far longer than storms or seasons. Volcanic outgassing did not respond quickly, but it did not stop easily either. When surface temperatures cooled and ice threatened to spread, volcanism continued, slowly adding carbon dioxide to the air. The atmosphere thickened, trapping more heat and resisting further cooling. In this way, volcanoes acted as a long-term stabilizer. They did not prevent short-term fluctuations, but they set a floor beneath which temperatures struggled to fall. Even when ice advanced and reflection increased, the slow accumulation of greenhouse gases provided a counterweight, nudging the climate back toward balance. The oceans played their part in this exchange. As carbon dioxide entered the air, some of it dissolved into seawater, interacting with rock at the seafloor. Over time, this removed carbon from the atmosphere, locking it into minerals. This removal worked gently and continuously, responding to rainfall, temperature, and circulation. The result was a slow conversation between interior, ocean, and sky. Volcanoes kept that conversation alive. Without them, carbon removed from the atmosphere would not be replaced. The planet would gradually lose its insulating blanket, becoming more vulnerable to cold with each passing age. Ice would spread more easily. Recovery would grow harder. In the early world, volcanism was more vigorous. Crust was thinner. Heat flowed more freely. Eruptions occurred not only at towering mountains, but along vast fractures in the seafloor hidden beneath young oceans. These underwater eruptions released carbon directly into the water, where it could later enter the atmosphere. The process was widespread, not concentrated, and it worked continuously. This mattered because it provided resilience. The climate did not depend on a single source of warmth. It rested on a network of slow processes, each reinforcing the others. Volcanoes supplied carbon. The atmosphere held heat. Oceans absorbed and redistributed energy. Together, they resisted the pull of permanent freeze. The importance of volcanism becomes clearer when imagining its absence. If internal heat had faded more quickly, or if the crust had sealed too effectively, carbon release would have slowed. The atmosphere would thin over long spans. Cooling would gain ground. Ice would spread with less resistance. Once volcanic outgassing drops below a certain pace, the balance shifts. Carbon removal continues through chemical reactions and sediment formation, but replacement lags behind. The sky grows clearer. Heat escapes more easily. The planet cools not in sudden steps, but in a steady drift toward stillness. This is not speculation. It is visible in worlds that lost internal heat early. Without sustained volcanism, their climates became fragile, then frozen. The surface records their last warmth in ancient features, now locked beneath ice or dust. Earth avoided this fate, in part because its interior stayed active. Plate movement allowed heat to escape gradually rather than abruptly. Melt continued to form and rise. Carbon continued to cycle. The planet remained dynamic, both above and below. In this context, volcanoes were not agents of chaos, but of continuity. Their eruptions reshaped landscapes, but their deeper role was quieter. They ensured that the atmosphere remained thick enough to hold warmth, even when other forces pushed toward cold. The early planet did not rely on chance bursts of activity, it relied on persistence. As long as volcanism endured, Earth retained a mechanism to counter long term cooling. The danger was never eliminated, but it was delayed, softened, and redirected. This slow exchange between fire and air became one of the planet's most important defenses. Not dramatic, not precise, but steady. In the long night of deep time, volcanoes kept breathing, and with each breath, they helped the world stay warm enough to continue. As heat rose from below and gases gathered above, another layer took shape between Earth and space. It was thin, shifting, and difficult to grasp, yet it carried enormous influence. Clouds drifted through the young sky, not yet governed by familiar patterns, responding to a world still assembling its climate. They were neither guardians nor threats by nature, but intermediaries, capable of tipping balance in either direction. Clouds reflect sunlight. Their pale surfaces send a portion of incoming energy back into space before it can reach the ground or sea. In this way, they cool a planet, softening the sun's influence. But clouds also trap heat. They absorb warmth rising from the surface and slow its escape, acting like a blanket drawn loosely across the sky. Whether clouds cool or warm depends on their height, thickness, and composition, as well as the color and temperature of the surface below. In Earth's earliest atmosphere, clouds behaved differently than they do today. The air contained no oxygen, no ozone, and far greater amounts of carbon compounds. Particles that serve as seeds for cloud formation were unlike those produced by modern life. Without dust from plants or aerosols shaped by biology, droplets formed around mineral grains, volcanic ash, and salts lifted from the young oceans. These early clouds likely hovered at different heights, spreading wider or thinner than their modern counterparts. Some may have formed higher in the atmosphere, where they trapped heat more effectively. Others spread low and broad, reflecting sunlight strongly. The balance between these types mattered deeply, because the planet operated close to its limits. A slight shift in cloud height or coverage could alter global temperature by degrees small enough to seem insignificant, yet large enough to change everything. More reflective clouds could cool the surface, encouraging ice to spread. More heat-trapping clouds could counter cooling, preserving liquid water. The difference lay not in dramatic transformations, but in subtle tendencies repeated over long spans. The early climate amplified these subtleties. With a faint sun and a surface vulnerable to ice, there was little room for error. Clouds did not need to change drastically to matter. A modest increase in coverage or thickness could tilt the balance toward cold. A small reduction could allow warmth to linger. Clouds also responded quickly to temperature. As the surface cooled, condensation increased, producing more clouds that reflected light and reinforced cooling. As the surface warmed, cloud patterns shifted, sometimes thinning, sometimes thickening, depending on altitude and chemistry. This responsiveness made clouds both stabilizing and destabilizing, depending on context. Unlike volcanic outgassing or chemical weathering, cloud behavior operates on short timescales. Clouds form and dissolve in hours or days, not millions of years. This makes them powerful but unpredictable. Their influence is immediate, but their long-term average effect is difficult to pin down. In the early Earth, this uncertainty was magnified by unfamiliar conditions. The absence of life meant fewer feedbacks that might regulate cloud formation. The composition of the atmosphere altered how droplets formed and how radiation moved through them. The young sun emitted light with a slightly different distribution, changing how clouds interacted with energy. All of this makes clouds one of the hardest elements of the early climate to reconstruct. The rocks preserve traces of temperature and chemistry, but clouds leave no direct record. Scientists infer their presence indirectly through models that simulate how air, water, and light interact under ancient conditions. These models are sensitive. Small changes in assumptions produce different outcomes. Adjust the size of droplets, and the balance shifts. Change the altitude of cloud layers, and temperatures respond. Increase or decrease cloud coverage by a small amount, and ice either advances or retreats. This sensitivity explains why clouds remain one of the largest uncertainties in understanding Earth's near misses with permanent freeze. They act at the edge of precision, where minor differences cascade into long-term consequences. In a stable modern climate, these variations are buffered. In the early world, they were decisive. Clouds also interacted with other processes. Volcanic eruptions injected particles that influenced cloud formation. Oceans supplied moisture that shaped their thickness. Ice below altered how much sunlight clouds needed to reflect to cause cooling. Each element intertwined with the others, creating a web of influence too complex to isolate cleanly. What emerges from this complexity is not confusion, but humility. The early climate was not governed by a single control knob. It was a system of interlocking parts, each sensitive to the others. Clouds occupied a central position in this system, acting as both shield and sieve, protector and risk. Their uncertainty does not weaken the story, it strengthens it. It reveals how narrow the margins were, how finely balanced the world remained. Earth did not survive its early challenges through simple mechanisms alone. It survived through a convergence of imperfect processes, clouds among them, drifting quietly across a sky that held the fate of oceans below. As the planet's systems pressed and balanced against one another, there existed a quiet boundary that mattered more than almost any other. It was not marked by mountains or oceans, but by latitude, a moving line across the surface where ice, once established, no longer behaved gently. Beyond this line, freezing did not merely spread, it accelerated. This boundary is often called the ice line. It marks the region where incoming sunlight weakens enough that ice gains an advantage over warmth. Closer to the poles, ice can persist seasonally without threatening the whole planet. But as it creeps toward lower latitudes, the geometry of sunlight changes. Light strikes the surface less directly. Reflection increases. Each new patch of ice sends more energy back into space than the darker ground it replaces. At this point, the climate begins to respond differently. Ice no longer advances step by step. It begins to reinforce itself. Cooling invites more ice. More ice reflects more light. The planet slips toward a new mode of behavior, one that resists reversal. Earth's deep history carries signs that this boundary was approached more than once. Certain ancient sediments reveal cycles of freezing that reached unusually far from the poles. Chemical traces in rock suggest that oceans cooled dramatically, while other layers indicate brief recoveries that halted the advance just in time. These records do not show a world comfortably distant from danger. They show hesitation. In these moments, Earth hovered near the ice line. Ice sheets expanded into regions where they had rarely lingered before. The surface brightened, temperatures fell further, yet the advance stalled. Something intervened, not dramatically, but persistently enough to slow the slide. Crossing this line would have altered the planet's behavior fundamentally. Once ice reached sufficiently low latitudes, the balance between sunlight absorbed and sunlight reflected would shift beyond easy repair. Even a strengthening sun or rising greenhouse gases would struggle to melt the expanding ice quickly. The surface would cool faster than it could recover. This is what makes the ice line so dangerous. It represents a tipping point rather than a gradual transition. On one side, the climate remains flexible. On the other, it locks into a state that favors ice dominance. The planet would not simply grow colder, it would reorganize itself around cold. In such a state, oceans would seal beneath thickening ice. Circulation between air and water would weaken, weather patterns would simplify. The removal of carbon dioxide through chemical processes would continue, but volcanic replacement might lag behind. The atmosphere would thin over long spans. Recovery would become increasingly unlikely. Evidence suggests that Earth never crossed this line fully during its earliest history, but the distance between safety and loss may have been narrow. Models indicate that a small shift in greenhouse gas concentration, a modest change in cloud behavior, or a slight reduction in volcanic output could have been enough to push ice past the threshold. What makes this unsettling is the scale of the margin. It was not wide, it was not forgiving. The planet did not enjoy a broad buffer of warmth. It lived close to the edge, where feedbacks waited quietly for an opportunity to take control. The rocks do not record panic or catastrophe, they record restraint. Ice advanced, then paused. Cooling deepened, then eased. The planet remained poised, neither retreating fully into warmth nor surrendering to freeze. This balance endured across immense spans of time, held together by overlapping processes that happened to counter one another closely enough. In this light, Earth's early climate resembles a slow negotiation rather than a stable agreement. Forces pulled toward cold, others resisted. The ice line marked the point where negotiation would end, where physics would no longer compromise. That Earth remained on the safer side of this boundary does not imply inevitability, it implies alignment. Greenhouse gases accumulated when needed. Volcanism continued to breathe carbon into the air. Clouds shifted in ways that did not overwhelmingly favor reflection. Oceans absorbed and redistributed heat. Each element contributed a small influence, and together they maintained balance. The narrowness of this margin defines the story. Earth did not wander casually near disaster. It traced its edge carefully, guided by processes that neither aimed nor foresaw the outcome. The ice line waited, silent and patient, a boundary that was never crossed, yet always close enough to shape the path forward. In the long stillness of geological time, this restraint mattered. It allowed the planet to continue changing rather than freezing into permanence. It preserved motion, water, and exchange. The ice line remained a reminder of how easily the world could have slipped and how quietly it managed not to. As time moved forward and the planet continued its long experiment in balance, Earth did not remain forever in that fragile middle ground. Long after its earliest oceans formed and its climate found temporary footing, the world slipped into episodes where ice nearly claimed everything. These moments stand as echoes of what almost happened much earlier, warnings written into stone rather than memory. During these later periods, ice advanced farther than it ever had before, not as scattered caps or seasonal sheets, but as a near global presence. Ice crept across continents, crossed latitudes once thought safe, and pressed toward the equator. The planet brightened under the sun, its surface reflecting more light than it absorbed. From space, Earth would have appeared pale and still. The geological record preserves unmistakable signs of these frozen ages. Ancient rocks show scratches carved by moving ice in regions that now lie near the tropics. Sediments deposited by glaciers rest beside layers that could only have formed in open water, revealing cycles of advance and retreat. These contradictions make sense only if ice once reached astonishing extents, then later withdrew. Other clues lie in chemistry. Certain rock layers contain signatures of cold oceans, while others above them show sudden warming. These transitions are abrupt on geological scales, suggesting that once ice took hold, the climate shifted into a different mode, one that resisted change until powerful forces intervened. During these Snowball Earth episodes, the oceans did not vanish, but they were hidden. Kilometers of ice sealed them off from the atmosphere. Sunlight struggled to penetrate the frozen shell. Wind could no longer stir surface waters. Exchange between ocean and air slowed to a near standstill. Beneath the ice, water remained liquid, warmed by heat from the planet's interior. Slow currents continued to move, carrying minerals and heat through the darkness. Life, where it existed, retreated into refuges near hydrothermal vents or beneath thinner ice at the margins. Survival depended on patience and isolation. Recovery from this state was extraordinarily difficult. Ice reflected most incoming sunlight, preventing warming from gaining traction. The atmosphere thinned as carbon dioxide was gradually removed by chemical processes, yet replacement from the interior continued. Volcanoes did not stop during these frozen ages. They kept releasing carbon dioxide, molecule by molecule, into an atmosphere that could no longer absorb it into oceans or soils. Over immense spans of time, this carbon accumulated. With oceans sealed, there was little opportunity for removal. The sky slowly thickened, becoming increasingly effective at trapping heat. This buildup was not fast. It unfolded over millions of years, a silent accumulation beneath an unchanging ice shell. Eventually, the balance tipped. Greenhouse warming overcame reflection. Ice began to thin. Once melting started, it accelerated. Dark water emerged, absorbing sunlight and amplifying warming. The planet shifted rapidly from deep freeze to intense heat, a transition as dramatic as the freeze itself. These episodes demonstrate how close Earth came to permanent lock. During Snowball Earth, the planet crossed many thresholds that earlier it had avoided. Ice reached low latitudes. Reflection dominated. The system resisted change strongly. Recovery required extraordinary buildup of greenhouse gases, far beyond ordinary levels. That recovery happened at all is remarkable. It depended on sustained volcanism, on the persistence of internal heat, and on the absence of mechanisms that might have removed carbon too efficiently. Any weakening of these processes could have left Earth frozen indefinitely. Snowball Earth stands as a proof rather than a possibility. It shows that global ice is not theoretical. It has happened. It shows how hard it is to reverse once established. And it shows how narrow the path of survival truly was. These frozen worlds were not gentle interludes. They reshaped the surface, altered chemistry, and tested every stabilizing force the planet possessed. They came closer to the edge than ever before, pressing against the limits of recovery. In the quiet after these ages, Earth carried the memory forward in its rocks. The scars of ice remained. The chemical traces lingered. The planet emerged, changed, but still moving, still warm enough to continue. Snowball Earth reveals that the danger of permanent freeze was never abstract. It arrived, nearly complete, and held on tightly. That the planet thawed again does not diminish the risk. It highlights the extraordinary convergence of processes required to escape. In the long story of Earth's climate, these frozen chapters stand as reminders of how close the world came to stillness, and how difficult it was to return from the brink once ice had nearly claimed everything. When ice wrapped the planet in near silence, life did not disappear. It withdrew. It moved inward, downward, and away from the hostile surface, following narrow paths where energy still flowed. Survival during these frozen ages depended not on abundance but on refuge. Beneath the vast ice sheets, the oceans remained liquid. The planet's interior continued to release heat, seeping upward through the crust and into the water below. This warmth was faint but steady, enough to prevent the seas from freezing solid. In these dark waters, far removed from sunlight, life persisted in forms that required little and endured much. Microbial communities clustered around places where heat and chemistry met. Along the seafloor, hydrothermal vents released warm, mineral-rich fluids into the surrounding water. These plumes carried energy from deep within the earth, creating small islands of activity beneath kilometers of ice. Here, microbes fed on chemical gradients rather than light, building ecosystems that moved slowly and quietly. Other refuges formed closer to the ice itself. In regions where ice thinned or fractured, faint light filtered through, meltwater trickled downward, carrying dissolved gases and nutrients. Microbes occupied these boundary layers, suspended between ice and ocean, adapting to extreme cold and long darkness. Their metabolism slowed, but they did not stop. Within the ice, tiny pockets of liquid water existed as well. Pressure and impurities lowered the freezing point, allowing microscopic films and channels to persist. In these narrow spaces, life clung to existence, shielded from crushing cold by the very ice that threatened it. Movement was limited, growth was rare, survival depended on patience. Heat from below played a central role in all these refuges. Without it, oceans would have frozen completely, and life would have lost its last shelter. The interior of the planet, still warm from formation and radioactive decay, became an unseen ally. Its energy traveled slowly upward, sustaining a thin layer of habitability beneath the frozen shell. Yet even these sanctuaries were fragile. They relied on a delicate balance of heat, chemistry, and time. If ice had thickened further, pressure could have altered ocean circulation, isolating refuges from nutrients. If internal heat had declined more rapidly, temperatures would drop below survivable limits. If chemical inputs weakened, energy sources would fade. The margin for survival was narrow. These ecosystems were not robust or expansive. They were constrained, vulnerable to disruption, and dependent on conditions remaining within tight bounds. Life endured not because the environment was forgiving, but because it was just tolerable enough. Communication between refuges was limited. Populations became isolated, separated by vast stretches of ice and dark water. Evolution slowed, diversity narrowed. Life entered a holding pattern, waiting without knowing for conditions to change. What makes this survival remarkable is not its resilience, but its restraint. Life did not conquer the frozen world. It did not reshape the climate or melt the ice. It endured quietly, leaving little trace. The planet did not recover because life fought back. It recovered because geological processes eventually shifted the balance. Had these refuges failed, the consequences would have been profound. A fully frozen planet without surviving life would not easily restart biological complexity. Even if ice later melted, the surface would emerge sterile. The long chain of evolution that followed would have ended before it began. Life's survival through near total freeze preserved continuity. It maintained a thread that could expand again when warmth returned. It ensured that when oceans reopened and skies softened, there were already living systems ready to respond, adapt, and diversify. This persistence did not guarantee success, it merely kept possibility alive. The difference between survival and extinction lay in small margins, in degrees of warmth, in the steadiness of internal heat, in the timing of thaw. In these frozen ages, life became a quiet passenger, carried forward by geology rather than driving it. It waited beneath the ice, in darkness and stillness, sustained by the slow heartbeat of the planet itself. When the ice finally began to retreat, life emerged not as a conqueror, but as a witness. Its survival marked the difference between a world that could continue to change and one that would remain forever silent. As ice advanced and retreated across the surface, and life waited patiently beneath frozen seas, another process continued almost unnoticed. It did not surge or collapse. It did not react quickly to storms or seasons. It moved instead at the pace of stone. This was the carbon cycle, Earth's slow safety valve, quietly linking rock, air, and ocean across immense spans of time. Carbon on Earth does not belong to any single place. It drifts between realms, changing form as it moves. Deep within the planet, it is locked inside minerals, pressed into crystal lattices by heat and pressure. Through volcanic activity, some of it escapes, rising into the atmosphere as gas. From there, it dissolves into rain, slips into oceans, and settles once more into rock. The journey is long, circular, and persistent. When carbon dioxide enters the air, it helps the planet retain warmth. When it leaves the air, temperatures slowly fall. The carbon cycle regulates this exchange not through precision, but through patience. It responds to climate, yet it does so gradually, often lagging far behind the changes it corrects. Weathering plays a central role in this balance. When rain falls through the atmosphere, it absorbs carbon dioxide, becoming slightly acidic. This rain then flows across exposed rock, reacting gently with minerals. Over time, these reactions break rock down and carry carbon into rivers and oceans. There, it becomes part of new minerals that settle on the seafloor, eventually returning to the planet's interior. This process strengthens when the climate is warm. Higher temperatures increase rainfall. Faster chemical reactions draw more carbon out of the air. As carbon dioxide declines, warming slows. When the climate cools, weathering weakens. Less carbon is removed from the atmosphere. Volcanic input continues, allowing greenhouse gases to build. Cooling slows, and warmth gradually returns. In this way, weathering acts as a stabilizer, not by preventing change, but by resisting extremes. It does not stop ice from forming or heat from rising. It ensures that neither state persists unchecked forever, provided the cycle remains intact. What makes this safety valve unusual is its time scale. Weathering does not operate on human lifetimes or even on the span of civilizations. It unfolds over hundreds of thousands to millions of years. Each grain of sand, each droplet of rain, contributes an almost immeasurable amount. Only over vast durations does the cumulative effect become visible. This slowness is both strength and vulnerability. It allows the planet to correct long-term trends without overreacting. But it also means that rapid disruptions can push the climate far from balance before the cycle responds. During sudden cooling events, ice can spread faster than weathering can compensate. During rapid warming, carbon can accumulate faster than removal allows. In Earth's early history, this slow pace mattered deeply. When the planet approached frozen states, the carbon cycle did not intervene immediately. Ice advanced, oceans sealed, life retreated. Only over long intervals did volcanic carbon accumulate enough to reverse the trend. Recovery required endurance, not speed. If the carbon cycle falls out of balance, the consequences are severe. Should weathering become too efficient, carbon dioxide could be stripped from the atmosphere faster than volcanism replaces it. The planet would cool steadily, becoming more reflective, more vulnerable to ice. If volcanism weakens too much, the same outcome follows. The safety valve would no longer hold pressure. On the other side, if weathering slows too much while volcanic release continues, carbon would build unchecked, temperatures would rise, oceans would warm, ice would vanish. Extremes would dominate in the opposite direction. Earth avoided these fates because its surface, oceans, and interior remained connected. Continents emerged to provide fresh rock for weathering. Rain continued to fall. Plate movement recycled carbon back into the mantle. No single component seized control for too long. The carbon cycle did not keep Earth comfortable. It kept Earth alive. It allowed the planet to wander near danger without remaining there permanently. It provided a delayed response, a long memory that carried climate back toward balance after disruption. In the frozen ages, this cycle was stretched to its limits. Ice slowed weathering almost to a halt. Carbon accumulated in the atmosphere, unseen beneath white skies. When thaw finally came, it came hard, driven by millions of years of stored imbalance. Through all of this, the carbon cycle remained indifferent to outcome. It did not protect life intentionally. It did not aim for stability. It simply followed chemistry and motion, slowly adjusting the planet's breath. This quiet process, almost invisible against the drama of ice and fire, became one of Earth's most important safeguards. Not because it was fast or precise, but because it never truly stopped. As Earth moved through cycles of warmth and cold, its climate was shaped not only by individual forces, but by how those forces responded to change. Some responses worked to soften extremes, others amplified them. These responses are known as feedbacks, and their direction mattered more than their size. Negative feedbacks act like quiet stabilizers. When temperatures rise, they introduce processes that cool the planet. When temperatures fall, they allow warmth to return. Weathering belongs to this category, slowly drawing carbon from the air when climates grow warm, then easing its grip as the world cools. Volcanic outgassing complements this by continuing to supply greenhouse gases when removal slows. Together, these processes resist runaway change, not quickly, but persistently. Positive feedbacks behave very differently. They do not resist change, they reward it. When a condition begins to shift, positive feedbacks push it further in the same direction. Cooling encourages more cooling. Warming invites more warming. Once engaged, these loops can overwhelm gentler stabilizers. Among all such processes, the ice albedo feedback stands apart in its danger. Ice reflects sunlight efficiently. As ice spreads, less energy is absorbed by the surface. Temperatures drop further. More ice forms. This loop requires no complex chemistry or long delays. It responds immediately to temperature changes and strengthens as ice expands. On a planet near its thermal limits, this feedback can dominate everything else. Even small advances of ice can trigger larger responses. Even modest cooling can become self-sustaining. Once ice reaches key latitudes, the loop accelerates, drawing the planet toward a frozen state that resists recovery. What makes this feedback especially threatening is its timing. Ice does not need to be thick or global to matter. It needs only to persist long enough in the right places. The geometry of sunlight ensures that ice at certain latitudes reflects far more energy than ice confined to polar regions. When the timing aligns, strength becomes secondary. This is where Earth's story becomes unusually delicate. Many of the planet's stabilizing processes operate slowly. Weathering adjusts over long spans. Carbon accumulates gradually. Internal heat changes at a glacial pace. Ice, by contrast, responds quickly. If cooling outpaces stabilizing feedbacks even briefly, ice can gain a foothold that becomes difficult to dislodge. Earth avoided permanent freeze not because its stabilizers were overwhelmingly strong, but because they were active at the right moments. Volcanic outgassing continued when ice advanced. Carbon accumulated beneath frozen skies. Clouds shifted without consistently favoring reflection. Oceans retained heat beneath ice, preventing total lock. The sequence mattered. Had volcanic activity declined before major glaciation, carbon buildup would slow. Had continents emerged differently, weathering might have stripped the atmosphere too efficiently. Had cloud patterns shifted slightly toward greater reflection during critical periods, ice could have advanced past recovery thresholds. None of these factors needed to fail completely. They needed only to misalign in time. A delay here, an acceleration there, could have allowed positive feedbacks to take control before negative ones responded. This is why Earth's survival cannot be attributed to a single protective mechanism. It depended on coordination without intention. Each process followed its own rules, unaware of the others. Their interactions happened to overlap in ways that preserved balance just long enough. In planetary terms, this is unusual. Many worlds experience feedbacks that reinforce one direction until change becomes permanent. Mars cooled as its atmosphere thinned. Ice persisted. Recovery never came. Icy moons froze early and remained so. Their feedbacks aligned toward stillness. Earth's feedbacks did not eliminate danger. They competed with it. For long stretches, the outcome was uncertain. Ice advanced and paused. Warming built and stalled. The planet hovered between states, shaped by forces that neither planned nor predicted the result. The idea of luck emerges naturally here, not as chance without cause, but as favorable timing among independent processes. Earth's internal heat lasted long enough. Its atmosphere retained gases long enough. Its surface evolved in a sequence that allowed stabilizers to remain active when they were most needed. Had these events occurred in a different order, strength alone would not have saved the planet. Timing was the deciding factor. The difference between a world that recovered and one that froze lay in when feedbacks engaged, not how powerful they were in isolation. In this way, Earth's climate history reads less like a controlled system and more like a narrow passage through competing influences. Positive feedbacks waited patiently, ready to accelerate collapse. Negative feedbacks responded slowly, offering resistance only if given time. That time was granted, again and again, by fortunate sequencing, not certainty, not inevitability. Just enough alignment to keep the story moving forward rather than ending in ice. As the planet moved along its narrow path between ice and warmth, the idea of closeness took on a meaning very different from everyday experience. On planetary scales, distance is not measured in kilometers or degrees alone. It is measured in stability. A world can appear calm while standing only a small step from irreversible change. Climate tipping points mark these boundaries. They are not gradual slopes, but thresholds where the behavior of a system shifts. On one side, feedbacks counter disturbance. On the other, they amplify it. The transition between these states can be subtle, invisible, until it has already occurred. Planets do not receive warning signs before crossing such points. There is no gradual signal that announces danger with clarity. Systems respond smoothly until they do not. Temperature may drift slowly, ice may expand quietly, gases may accumulate gently, all without obvious alarm. Then, a limit is reached, and the response changes character. This is because feedbacks operate continuously, but their influence depends on context. As long as stabilizing feedbacks remain effective, change appears manageable. Once amplifying feedbacks gain the upper hand, the same rate of change produces far larger consequences. The planet behaves differently, even though the external forces may not have shifted dramatically. Earth's geological record captures moments when this boundary was approached. Layers of rock preserve evidence of rapid transitions, where conditions shifted faster than surrounding periods. Ice indicators appear suddenly at low latitudes. Chemical signatures show abrupt cooling or warming. These features suggest near crossings, moments when the system leaned heavily toward one outcome before being pulled back. Such records do not reveal exact distances from tipping points. They reveal proximity through behavior. When changes accelerate, when recovery becomes difficult, when conditions linger near extremes, scientists infer closeness. These are indirect measures, shaped by interpretation and incomplete data. Certainty remains out of reach because the past does not provide controlled experiments. The planet cannot be rewound and tested under slightly different conditions. Each event unfolded once, influenced by countless interacting factors. Some left traces, others vanished without record. This uncertainty is not a flaw in understanding, it is a reflection of how planetary systems work. They are complex, sensitive, and history dependent. Small differences in timing or magnitude can lead to different outcomes, even when starting conditions appear similar. When scientists say Earth came close to permanent freeze, they are not pointing to a precise number or moment. They are describing a pattern of behavior consistent with systems nearing critical thresholds. Ice spread farther than expected. Recovery required extraordinary circumstances. Stabilizing forces barely kept pace with destabilizing ones. The lack of warning signs makes these near crossings especially significant. The planet did not signal distress in obvious ways. There were no clear markers that would have allowed prediction. The system responded only when thresholds were met, and by then, recovery was already difficult. This has implications beyond Earth. Other worlds may appear stable for long periods, only to cross tipping points suddenly. Their histories may record long, calm intervals punctuated by irreversible change. From a distance, these planets might seem habitable until they are not. On Earth, the evidence suggests repeated brushes with such boundaries. Each time, the outcome depended on the alignment of slow processes rather than on dramatic intervention. Volcanic outgassing continued. Carbon accumulated. Ice retreated. The planet stepped back from the edge without ever clearly announcing how close it had been. Why certainty is impossible lies in the nature of the record itself. Rocks tell stories, but not with complete sentences. They preserve conditions, not counterfactuals. They show what happened, not what nearly did. To estimate closeness, scientists compare observations with models, each carrying assumptions and limits. Models help explore possibilities, revealing how small changes might have altered outcomes. They show how close thresholds can be under certain conditions, but models are simplifications. They cannot capture every interaction or unknown factor. Their conclusions remain ranges, not absolutes. In this space between evidence and interpretation, Earth's near misses reside. The planet's history suggests repeated approaches to irreversible states without crossing them. The distance from those states cannot be measured precisely, only described as narrow. This narrowness defines the story. Earth did not occupy a wide basin of safety. It traced a thin line through possibility, guided by feedbacks that sometimes resisted change and sometimes nearly surrendered to it. Understanding how close is close in planetary terms means accepting uncertainty as part of the picture. It means recognizing that survival does not require large margins, only enough alignment to avoid crossing a threshold. Earth's past reveals a world that lived close to the edge without ever fully stepping beyond it, a testament not to certainty, but to the delicate nature of balance itself. As Earth continued to walk its narrow path between ice and warmth, another world nearby followed a different course. Mars formed from similar materials under the same young sun, yet its story diverged quietly and permanently. Understanding why Earth remained active while Mars grew cold reveals how subtle physical differences can decide planetary fate. Size mattered from the beginning. Earth is larger and more massive, and that extra mass carries consequences that unfold over billions of years. Greater gravity allowed Earth to hold on to its atmosphere more effectively. Gases released from volcanoes lingered, accumulating rather than drifting away. On Mars, weaker gravity made it easier for gases to escape into space, thinning the sky over time. This difference shaped everything that followed. An atmosphere acts as a blanket, slowing the loss of heat from a planet's surface. Earth's thicker air retained warmth, helping to stabilize climate even when sunlight was limited. Mars, with its lighter grip, lost this protection gradually. Each lost molecule reduced its ability to trap heat, nudging the planet toward cold. Internal heat played a similar role. Earth's larger size meant it cooled more slowly. Heat generated during formation and from radioactive elements remained trapped longer within the interior. This sustained warmth kept the mantle active, allowing magma to rise and volcanoes to erupt over vast spans of time. Through this activity, carbon dioxide and other gases continued to replenish the atmosphere. Mars, smaller and cooler, lost internal heat more quickly. Its mantle solidified earlier. Volcanic activity waned. With fewer eruptions, there was little to replace gases lost to space. The carbon cycle stalled. Without replenishment, the atmosphere thinned further, accelerating cooling. As Mars cooled, its surface conditions changed. Water that once flowed across the landscape became unstable. Without sufficient atmospheric pressure and warmth, liquid water could not persist. Ice formed and remained. Chemical weathering slowed. Feedbacks that might have moderated climate weakened or disappeared. Atmospheric escape compounded these effects. High-energy particles from the sun interacted with the upper atmosphere, stripping away gases over time. Earth's magnetic field provided protection, deflecting much of this energy and preserving the atmosphere. Mars, with a weaker or absent global magnetic field, remained exposed. The slow erosion of its sky continued unchecked. These processes did not unfold in isolation. Each loss made the next more likely. Thinner air meant cooler temperatures. Cooler temperatures meant less volcanic activity and less water-driven weathering. Reduced activity meant fewer gases returned to the atmosphere. The system leaned steadily toward cold. Mars crossed a line Earth avoided. Once its atmosphere fell below a certain thickness, recovery became unlikely. Even if volcanic activity resumed briefly, it would not restore the lost pressure quickly enough. Ice, once established, reflected sunlight and reinforced cooling. The planet settled into a stable, frozen state. Earth approached similar boundaries, but never crossed them fully. Its size allowed it to retain heat and air longer. Its interior remained active enough to sustain volcanic outgassing. Its magnetic field shielded the atmosphere from erosion. These advantages were not dramatic in any single moment. They accumulated quietly, their effects revealed only over immense spans of time. This difference does not suggest that Earth was immune to freezing. It suggests that Earth had more time for stabilizing feedbacks to respond, more time for carbon to accumulate beneath ice, more time for warmth to return before thresholds were crossed. Mars did not fail suddenly. It cooled gradually, passing points of no return without ceremony. Rivers dried, atmosphere thinned, ice spread. Each step followed naturally from the last. There was no single catastrophe, only a slow drift toward stillness. Looking back, the contrast between the two worlds underscores how narrow Earth's margin truly was. A slightly smaller mass, a slightly faster cooling interior, a weaker magnetic field, and the outcome could have been different. The planet did not need to be radically altered to fail. It needed only to resemble Mars a little more closely. Earth's survival was not guaranteed by its position alone. It depended on a combination of size, gravity, heat, and protection that happened to align favorably. Mars serves as a reminder that planets sharing the same star can experience vastly different destinies. In the quiet comparison between these two worlds, the lesson is subtle. Stability emerges not from strength alone, but from persistence. Earth persisted just long enough, retaining its warmth and breath, while Mars let them slip away. As Earth retained its atmosphere and internal warmth, another guardian worked quietly across the surface. The oceans, vast and deep, became more than reservoirs of water. They became storehouses of heat, smoothing extremes and slowing the planet's drift toward ice. Water has an unusual ability to absorb warmth without changing temperature quickly. As sunlight reached the surface, oceans took in energy and held it, releasing it slowly over time. This buffering softened the contrast between day and night, between seasons, and between regions. Where land might cool rapidly, water lingered in warmth. On early Earth, this effect was even more important. With a faint sun and a climate prone to instability, any process that delayed heat loss mattered. Oceans acted as thermal memory. Heat gathered during warmer intervals remained available during colder ones, reducing the speed at which ice could spread. Depth amplified this effect. Early oceans were not shallow films. They sank deep into the crust, covering much of the planet. The deeper the water, the greater its capacity to store heat. Warmth absorbed near the surface slowly mixed downward, distributing energy through vast volumes. Once stored at depth, heat became difficult to remove. This vertical movement depended on density differences driven by temperature and chemistry. Warmer, lighter water floated above colder, denser layers. As surface waters cooled, they sank, carrying heat downward while bringing colder water up. This slow overturning circulated energy through the ocean, preventing it from concentrating at the surface where it could escape quickly. Circulation patterns on early Earth differed from those of today. Continents were smaller or absent, allowing currents to flow more freely around the globe. Without major land barriers, water could redistribute heat efficiently from equatorial regions toward higher latitudes. This movement helped counter the tendency of polar regions to freeze permanently. Salinity also played a role. Chemical interactions between water and rock added dissolved minerals to the ocean, altering density and influencing circulation. These subtle differences shaped currents, guiding heat through pathways invisible at the surface. Together, these processes created a planetary heat engine that worked continuously. Sunlight entered at the surface, heat moved through the ocean, and energy was released slowly back to the atmosphere. This cycle did not prevent cooling entirely, but it slowed it, buying time for other stabilizing processes to respond. The presence of open water also influenced clouds and weather. Evaporation added moisture to the air, affecting cloud formation and precipitation. These interactions further modulated temperature, linking ocean behavior to atmospheric dynamics. When oceans remain liquid, they act as active participants in climate. When they freeze, that participation diminishes sharply. Ice seals the surface, cutting off direct exchange between water and air. Heat stored below becomes trapped, unable to influence surface temperature. Circulation slows as stratification increases beneath the ice. As ice thickens, sunlight struggles to penetrate. The ocean's ability to absorb new energy weakens. Reflection dominates. The heat storage system effectively shuts down at the surface, leaving only internal heat to sustain liquid water below. In such conditions, the stabilizing influence of the oceans fades. Without open water, the planet loses a key buffer against rapid cooling. Feedbacks favor ice expansion. Recovery becomes more difficult. Earth's history includes moments when oceans approached this frozen state. During near global glaciations, open water persisted only in limited regions. Heat storage continued beneath ice, but its influence on surface climate diminished. These periods revealed how dependent the planet was on liquid oceans for stability. The survival of even small areas of open water made a difference. Dark surfaces absorbed sunlight. Exchange resumed. Circulation restarted. These openings acted as anchors, preventing complete shutdown of the heat storage system. In this sense, the oceans were not merely passive. They resisted freezing by holding warmth, by moving it, and by reconnecting surface and depth whenever possible. Their depth and extent gave them inertia, a resistance to change that surface processes lacked. Earth's ability to avoid permanent freeze relied in part on this inertia. The oceans did not respond instantly to cooling. They released stored heat slowly, opposing rapid transitions. This delay allowed greenhouse gases to accumulate and feedbacks to shift before ice could claim everything. The role of the oceans as heat storage reveals another layer of Earth's narrow survival. Without deep, circulating seas, the planet would have lost warmth more quickly and recovered more slowly. The difference between a frozen world and a living one lay, in part, in the quiet capacity of water to remember heat and share it gently across time. As oceans stored heat and released it slowly back into the air, another process worked even more quietly beneath the surface. It did not act through storms or sunlight, but through motion so slow it is almost invisible in a human lifetime. The shifting of Earth's crust, known as plate tectonics, became one of the planet's most important climate guardians without ever announcing itself. Earth's surface is not a single solid shell. It is divided into moving plates that drift, collide, separate, and sink. This motion reshapes the planet gradually, lifting continents, opening oceans, and closing others. Over deep time, these movements determine where land sits beneath the sky and that placement matters for climate. As continents move, they change how rock is exposed to air and rain. Fresh rock lifted from below reacts readily with carbon dioxide dissolved in rainfall. This process removes carbon from the atmosphere and stores it in minerals. When continents spread wide and mountains rise, weathering increases, carbon drawdown strengthens, temperatures slowly ease. When continents cluster or lie low, weathering weakens, less fresh rock meets rain, carbon remains in the air longer, warmth builds gently. In this way, plate motion adjusts the planet's long-term thermostat, not precisely, but persistently. Mountain building plays a special role in this balance. When plates collide, crust thickens and rises. Vast ranges form, exposing enormous surfaces of fresh rock. Rainfall across these slopes accelerates chemical reactions that remove carbon dioxide from the atmosphere. Over millions of years, this drawdown can cool the planet significantly. Yet this cooling is not permanent. As mountains erode, the carbon locked within minerals is carried to the oceans and eventually returned to the mantle through subduction, where one plate slides beneath another. Deep below, heat and pressure reset the cycle. Carbon is stored again, waiting to be released through future volcanism. This continuous recycling keeps the carbon cycle alive. It ensures that removal and replacement remain connected. Without this connection, imbalances would persist. The planet would drift toward extremes. A dead planet lacks this motion. Without plate tectonics, continents remain fixed. Fresh rock is not uplifted regularly. Weathering slows. Carbon once removed from the atmosphere stays locked away. Volcanic recycling weakens. Over time, the atmosphere thins, heat escapes more easily, and the planet cools. Mars offers a glimpse of this outcome. With little or no active plate tectonics, its surface froze into place. Volcanism declined, carbon cycling stalled, cooling became irreversible, ice remained, and recovery never followed. Earth avoided this fate through an unusual tectonic advantage. Its size allowed internal heat to persist long enough to drive plate motion. Its crust remained flexible rather than rigid. Water within the mantle lowered melting temperatures, aiding movement and lubrication. These factors combined to sustain tectonics across billions of years. This longevity mattered. It meant continents continued to move even as the sun brightened and climates shifted. It meant weathering could respond to warming and volcanic release could respond to cooling. The system did not require precision, only continuity. During periods when Earth approached deep freeze, plate tectonics quietly prepared recovery. As ice spread and weathering slowed, volcanic carbon accumulated. As mountains eroded beneath ice and rain, carbon eventually returned to circulation. The cycle never stopped completely, even when surface conditions were harsh. The presence of continents themselves depended on tectonics. Without plate movement, continental crust would not persist. Oceans would dominate. Weathering patterns would differ dramatically. The balance between land and sea would shift, altering heat absorption, circulation, and atmospheric chemistry. Earth's tectonic behavior also created diversity of environments. Some regions uplifted, others sank. Some weathered rapidly, others remained stable. This variation prevented uniform extremes. The planet never became too efficient at cooling or too inefficient at warming for too long. What makes plate tectonics remarkable is its indirect influence. It does not control climate day to day. It shapes the stage on which climate unfolds. Its effects are delayed, cumulative, and profound. Earth's survival near the edge of permanent freeze depended on this hidden motion. Without it, stabilizing feedbacks would weaken over time. the planet would lose its ability to recover from deep cold. Ice would linger. Reflection would dominate. Plate tectonics did not guarantee safety. It provided opportunity. It kept pathways open between rock, ocean, atmosphere, and interior. It allowed Earth to adjust slowly rather than lock abruptly. In the long dream of deep time, this slow shifting of stone became one of the planet's quietest protectors, guarding warmth not by force, but by motion that never fully ceased. After ice retreated and oceans reopened, Earth entered stretches of calm that can feel reassuring when viewed from a distance. The climate settled into long periods where temperatures changed slowly, seas remained open, and the sky behaved predictably. These were not moments of drama or collapse. They were quiet spans, measured in millions of years, where the planet appeared to have found its footing. Yet this calm carried its own risk. Extended stability does not mean safety. In planetary systems, stability often signals balance, but it can also signal tension held in place by delicate alignment. During these long, quiet periods, Earth rested within narrow bounds. The processes that warmed and cooled the planet were still active, still pulling in opposite directions, but they happened to cancel each other closely enough to produce calm. The danger lay in how little slack remained. When a system sits far from its limits, disturbances fade. When it sits near a boundary, even small disruptions can matter. During these stable phases, Earth hovered close to thresholds, shaped by ice reflectivity, greenhouse gas levels, and ocean circulation. The planet looked steady because opposing forces were matched, not because those forces were weak. In such conditions, change did not need to be dramatic to be consequential. A modest decline in volcanic output could allow carbon dioxide to fall just enough to favor cooling. A shift in continental position could alter weathering patterns, quietly drawing more carbon from the air. A rearrangement of ocean currents could move heat away from regions already near freezing. None of these changes would announce themselves loudly. They would unfold slowly, almost invisibly, yet their effects would accumulate. Stability became dangerous because it encouraged persistence. Ice did not need to advance rapidly to matter. It needed only to persist slightly longer than usual. Clouds did not need to reflect vastly more sunlight. They needed only to favor cooling just enough, just long enough, for feedbacks to strengthen. During these calm intervals, Earth's climate lacked the urgency that drives rapid correction. Volcanic carbon release continued, but without obvious imbalance to counter, its influence remained subtle. Weathering continued, quietly removing carbon as it always had. Oceans circulated heat efficiently, masking slow drifts in temperature. This masking effect mattered. It allowed underlying trends to develop without obvious surface signals. The planet could drift closer to danger while appearing unchanged. Geological records from these periods often show long, uniform layers, indicating steady conditions. But beneath this apparent sameness, small variations appear. Slight changes in isotope ratios, subtle shifts in sediment composition. These hints suggest that the climate was not fixed, only restrained. The risk was cumulative. Each small disruption did not need to be catastrophic. It needed only to align with others. A slight cooling paired with reduced atmospheric protection, a small increase in ice coverage combined with altered cloud behavior. Over time, these alignments could push the system toward a tipping point. Earth had little room to spare. The margin between a stable ocean world and a frozen one was thin. The planet's history shows that when this margin narrowed too much, recovery required extraordinary circumstances, long spans of carbon accumulation, and significant internal heat. What protected Earth during these quiet periods was not strength, but continuity. Volcanism did not cease, plate movement did not stop, oceans did not freeze entirely. Each process continued just enough to prevent small drifts from becoming permanent slides. But the balance remained precarious. Stability did not reset the system to safety. It held the system in place while time passed. In this way, the long quiet periods represent some of the most vulnerable moments in Earth's story, not because they were violent or chaotic, but because they relied on alignment rather than resilience. The planet survived not by being far from danger, but by not being nudged too hard, too often, in the wrong direction. These phases remind us that planetary failure does not require catastrophe. It can arrive through patience, through the steady accumulation of small changes that go unnoticed until a threshold is crossed. Earth endured these stretches by remaining just active enough, just dynamic enough to keep correcting itself. The room it had to spare was measured not in comfort, but in timing. A few processes continuing a little longer, a few disruptions arriving a little later. In the long stillness of deep time, this restraint made all the difference. As life spread across oceans and continents, it began to shape the planet in visible ways. Chemistry shifted, gases cycled differently, new feedbacks emerged between biology and climate. Yet, the presence of life did not place Earth beyond danger. It added influence, not immunity. Living systems interact with climate, but they do not command it. Microbes altered the composition of the atmosphere. Later organisms changed how carbon moved through air and water. These changes mattered, but they remained part of a larger system governed by physics, chemistry, and time. When conditions shifted far enough, biological influence could be overwhelmed. There were moments when life expanded its reach, stabilizing climate indirectly. Photosynthetic organisms reduced certain gases and released others, reshaping atmospheric balance. Over long spans, these changes affected temperature and circulation. Yet these processes worked slowly, and they depended on environments remaining within narrow bounds. Feedbacks outside biology often moved faster. Ice spread more quickly than ecosystems could respond. Volcanic emissions could rise or fall independently of living systems. Changes in orbit and continental position altered climate without regard for what lived on the surface. When these forces aligned, biology adapted or retreated, but it did not decide the outcome. Earth's history contains periods when life nearly lost control of its environment. During deep freezes, ecosystems collapsed into refuges. During extreme warming events, oceans lost oxygen and vast regions became inhospitable. These episodes show that life can persist through hardship, but not without cost. The relationship between life and climate is not one of mastery, but of negotiation. Living organisms modify their surroundings, but they rely on conditions that allow those modifications to matter. When ice seals oceans or heat strips oxygen from water, biology becomes a passenger rather than a driver. There were times when life amplified climate change unintentionally. The buildup of oxygen transformed atmospheric chemistry, altering greenhouse behavior and contributing to cooling. These changes reshaped the planet in ways that life then had to endure. The feedbacks created by biology did not always favor stability. At other times, life softened extremes. Vegetation enhanced weathering, drawing carbon from the air. Microbial processes influenced cloud formation. These effects helped regulate temperature, but only when the system remained within reach of those influences. Beyond certain thresholds, physics regained dominance. Survival after life began depended on timing and alignment, not on biological control. Life had to persist long enough for geological processes to counter extreme shifts. When those processes lagged, ecosystems suffered, extinctions followed. Recovery required both biological resilience and favorable physical conditions. Earth avoided complete failure after life arose because stabilizing forces continued to operate alongside biology. Plate tectonics recycled carbon, volcanoes replenished the atmosphere, oceans stored and redistributed heat. Life contributed, but it was never alone in maintaining balance. This interdependence meant that survival was never guaranteed. Each major shift tested whether biological and geological feedbacks would align or conflict. At times, they worked together. At other times, they pulled in opposite directions. The planet's resilience emerged from overlap, not hierarchy. No single system held authority. Climate shaped life, life shaped climate, geology shaped both. When one faltered, others sometimes compensated. When several faltered at once, the margin narrowed dangerously. The record of near failures remains etched in stone and chemistry. Layers mark sudden losses, gaps signal collapse. These traces remind us that life's presence did not smooth Earth's path, it complicated it. In the long view, survival appears less like inevitability and more like persistence under constraint. Life endured not because it controlled the planet, but because it adapted repeatedly to conditions that could have ended it. Earth continued because physical processes eventually restored balance after disruptions, allowing biology to expand again. Had those processes weakened or mistimed, life's influence would not have been enough. The story that emerges is not one of triumph over nature, but of endurance within it. Life did not secure Earth's climate. It navigated it, surviving close calls and narrow margins, never guaranteed a future, only another chance to continue. As Earth continued to change, its memory did not vanish with time. It settled instead into stone. Layer by layer, the planet recorded its own conditions, not as stories or images, but as subtle patterns embedded in rock. These records are incomplete and silent, yet they remain the most faithful witnesses to climates long gone. Ancient sediments formed wherever water slowed enough to let particles fall. In oceans, lakes, and shallow seas, grains of minerals settled gently, creating thin layers that stacked over time. Each layer carried traces of the environment in which it formed. Grain size reflected energy and movement. Chemical composition reflected the water that surrounded it. Together, these layers became a slow archive of changing conditions. Some sediments tell of cold. They contain fragments dropped by melting ice, carried far from their source by drifting glaciers. Others tell of warmth, showing signs of chemical reactions that occur only when liquid water circulates freely. The alternation of these layers reveals cycles of advance and retreat, moments when ice spread and moments when it withdrew. Beyond visible structure, rocks carry more delicate information. Atoms themselves shift in predictable ways as temperature changes. Certain elements come in slightly different forms, known as isotopes. These forms behave almost identically, yet they separate subtly under different conditions. When water evaporates, freezes, or rains, isotopes sort themselves in small but measurable patterns. Locked into minerals and shells, these isotopic ratios endure. Long after oceans vanish and ice melts, the ratios remain, preserving a chemical memory of temperature. By reading these patterns, scientists infer whether ancient waters were warm or cold, whether ice was present nearby, whether evaporation or freezing dominated the cycle. Reconstructing deep time from these clues is an act of careful interpretation. No single rock tells a complete story. Scientists compare layers from different regions, align them by age, and search for consistency. They use models to test whether proposed conditions could produce the observed signatures. Over time, a picture emerges, not sharp or complete, but coherent enough to guide understanding. This reconstruction requires patience. Rocks are altered by pressure, heat, and movement. Some layers are buried deeply and transformed. Others are eroded away entirely. Gaps appear where records should exist. Time compresses in places and stretches in others. What remains is partial, shaped by survival as much as by formation. Certain moments are preserved clearly, others are lost forever. When ice advanced rapidly and retreated quickly, it may leave only a thin trace, or none at all. When sediments formed in environments later destroyed by tectonic motion, their record vanished with them. Entire chapters of climate history were erased before they could harden into stone. This absence is itself meaningful. It reminds us that the planet's memory is selective. The rocks do not record every fluctuation or near miss. They preserve conditions that lasted long enough and occurred in places where preservation was possible. Short-lived crises may leave faint or ambiguous signals. Because of this, certainty remains elusive. Scientists do not reconstruct the past by reading a single line, but by weighing many imperfect lines together. Confidence grows through convergence rather than completeness. When different records point toward the same conditions, trust strengthens. When they diverge, uncertainty remains. What the rocks still remember is not exact temperature curves or precise timelines. They remember direction. They remember extremes. They remember transitions that altered the planet's behavior for long enough to leave an imprint. In the context of near-permanent freeze, this matters deeply. The rocks show repeated approaches to cold states. They show ice appearing in unexpected places. They show chemical conditions consistent with restricted oceans and altered circulation. These signals suggest closeness to thresholds, even when the precise distance cannot be measured. What is missing forever are the moments just before crossing. The final steps toward irreversible change may leave no record if they are brief. A planet can approach failure without carving that approach into stone. The absence of evidence does not imply safety, it implies silence. This limitation shapes how Earth's story is told. Scientists infer danger not from catastrophe alone, but from patterns that indicate strain. When records show repeated stress without collapse, they suggest resilience, but also proximity to limits. The rocks do not speak in absolutes. They whisper in ratios, layers, and textures. They remind us that Earth's survival was not recorded in full detail, only in fragments that endured. From those fragments, a story emerges of balance, tested repeatedly, preserved imperfectly, and remembered just enough to show how close the planet came to losing everything. As the evidence accumulated and the story of near failure took shape, agreement did not settle in quietly behind it. Instead, debate followed, persistent and careful. Scientists still argue about how close Earth truly came to permanent freeze, not because the question lacks importance, but because the answers depend on layers of uncertainty that cannot be fully peeled away. At the heart of this debate lie competing climate models. These models are mathematical reconstructions of how energy, gases, water, and ice interact across a planet. Each model is built from the same physical principles, yet they differ in how those principles are combined. Small choices, such as how clouds are represented or how heat moves through oceans, lead to different outcomes when projected across deep time. Some models suggest that early Earth required extremely high greenhouse gas levels to remain warm under a faint sun. Others find that more modest concentrations could suffice when combined with certain cloud behaviors or ocean circulation patterns. Both approaches can match parts of the geological record. Neither can match all of it perfectly. The uncertainty deepens when models attempt to simulate feedbacks near tipping points. Ice growth, cloud formation, and atmospheric chemistry interact in ways that are difficult to capture precisely. Slight changes in assumptions can shift the outcome from survivable to frozen. This sensitivity does not imply error. It reflects the real fragility of the system being modeled. Early atmospheric data adds another layer of difficulty. The composition of Earth's ancient sky cannot be measured directly. It must be inferred from rocks that interacted with that air long ago. These rocks preserve hints, but not complete inventories. Ratios of elements suggest ranges, not exact values. The presence of certain minerals implies conditions, but not their duration or intensity. Methane levels, for example, depend on assumptions about geological activity and chemical reactions that no longer operate in the same way. Carbon dioxide estimates vary, depending on how efficiently it was removed by weathering or dissolved in oceans. Oxygen was absent or rare, but its exact timing and influence remain debated. Because these inputs feed directly into climate models, uncertainty compounds. A small change in assumed atmospheric composition can alter predicted temperatures significantly. As new data emerges or interpretations shift, models are adjusted and conclusions change with them. This is why answers evolve over time. As analytical techniques improve, scientists extract finer details from rocks once thought exhausted. New simulations run faster and explore broader possibilities. Old assumptions are revisited. Conclusions that once seemed firm soften, then sharpen again in new forms. This process is not a sign of weakness, it is how understanding advances in systems as complex as planetary climate. Each generation refines the picture, not by discarding the past, but by re examining it with better tools. Yet, some questions may never be resolved completely. The precise moment when Earth was closest to permanent freeze may be lost to erosion. The exact thickness of ice at critical times may never be known. The detailed structure of early clouds may remain beyond reconstruction. The rocks cannot record everything. Short-lived extremes leave faint traces or none at all. Processes that occurred globally, but briefly, may escape detection. The planet's memory is partial, shaped by what survived burial, heat, and time. This means that debates will persist, not because scientists disagree on fundamentals, but because the available evidence supports multiple interpretations within reasonable bounds. Earth could have been one small change from failure, or several. Both possibilities fit parts of the record. What remains consistent is the broader pattern. Earth did not enjoy a wide margin of safety. It navigated a narrow corridor shaped by interacting feedbacks. It avoided permanent freeze not by overwhelming stability, but by alignment that held just long enough. Scientific disagreement refines this picture rather than undermining it. Each argument tests the limits of what is plausible. Each model explores a different path the planet might have taken. Together, they map the space of possibility, even if they cannot pinpoint a single truth. In this sense, uncertainty becomes part of the story itself. It mirrors the planet's own precarious history. Just as Earth balanced near thresholds without clear signals, scientists work near the edge of what evidence allows, careful not to claim certainty where none exists. What may never be resolved is not whether Earth survived by chance or design, but exactly how narrow that survival was. The rocks remember enough to show danger. they do not remember enough to measure it precisely. And so the argument continues, quietly and patiently, much like the processes it seeks to understand. As Earth's long story unfolded, one pattern became quietly clear. Planetary fate is not decided only by dramatic forces or rare catastrophes. It is shaped by small changes, accumulated patiently, amplified by timing, and guided by context. The difference between survival and failure often rests not on magnitude, but on alignment. Slight shifts in gas levels illustrate this clearly. A modest increase in carbon dioxide can warm a planet just enough to prevent ice from advancing. A modest decrease can allow cooling to deepen and reflection to take hold. These shifts do not need to be extreme, they need only to persist. Over thousands or millions of years, small imbalances compound, nudging climate toward a new state. On early Earth, greenhouse gases hovered within narrow ranges. Volcanic release, chemical removal, and ocean absorption continually adjusted their levels. At times, the balance leaned slightly warm. At other times, it leaned slightly cold. Each lean mattered. When the planet drifted toward cold, ice responded quickly. When warmth returned, recovery required patience. Orbital differences add another subtle influence. The shape of a planet's path around its star, the tilt of its axis, and the timing of its seasons affect how sunlight is distributed across the surface. Even minor variations can change where ice forms and how long it lasts. These changes do not alter total energy received dramatically, but they redistribute it in ways that favor or resist ice growth. A slightly lower axial tilt concentrates sunlight near the equator, allowing polar regions to cool more deeply. A slightly different orbit alters the balance between seasons, extending cold intervals or shortening warm ones. On a planet near its limits, these adjustments can tip the scales. What matters most is timing. A small change arriving at the wrong moment can outweigh a larger change arriving later. If greenhouse gas levels dip during a period when ice already threatens to expand, the combined effect can accelerate freezing. If the same dip occurs during a warmer interval, it may pass unnoticed. Earth's history shows repeated instances where timing saved the planet. Volcanic carbon accumulated when ice sealed oceans, not before. Continental weathering intensified when warmth increased, not when cooling dominated. Ocean circulation redistributed heat during vulnerable periods, not after thresholds were crossed. The magnitude of these influences was often modest. None alone guaranteed survival. Their effectiveness depended on when they acted relative to other forces. A strong stabilizing feedback that arrives too late fails. A weaker one that arrives early enough succeeds. This sensitivity to timing makes planetary survival fragile. It suggests that Earth's outcome was not a simple consequence of its size or position. It depended on sequences of events unfolding in favorable order. A small delay here, a slight acceleration there, and the path could diverge. This has implications for other worlds. Many planets may possess liquid water briefly or experience partial stability, only to lose it later. Their histories may differ from Earth's by small margins that lead to large consequences. The conditions that allowed Earth to persist may be uncommon, not because the ingredients are rare, but because the timing is difficult to reproduce. Earth's survival may not be repeatable even under similar circumstances. Another planet with the same mass, atmosphere, and distance from its star could still fail if its internal heat declines faster, if its continents assemble differently, or if its orbital variations align unfavorably. This does not mean Earth's history was miraculous. It means it was contingent. The planet followed a path through possibility space that remained open just long enough. Many neighboring paths led to frozen stillness. Earth stayed between them. The idea that small changes decide planetary fate reframes how stability is understood. Stability is not the absence of change, it is the presence of counteracting changes that arrive at the right times. Remove one or shift its timing, and the balance dissolves. In Earth's case, survival depended on a chain of near successes. Each link held, not because it was unbreakable, but because pressure did not arrive all at once. Ice advanced, but greenhouse gases rose. Cooling deepened, but internal heat persisted. Thresholds loomed, but feedbacks responded before crossing. This narrow passage does not guarantee permanence. It reveals how easily the story could have ended differently. Earth's long habitability rests on accumulated small advantages, each one insufficient alone, yet decisive together. In the quiet sweep of deep time, it was not grand forces that decided the outcome. It was the patient influence of slight shifts, well timed, shaping a future that remained open rather than frozen. As Earth continued along its narrow path, the wider universe followed many different ones. Beyond our planet, worlds formed under similar laws of physics and chemistry, yet their stories diverged sharply. Some cooled too quickly, others froze and never returned. In these distant outcomes, Earth's survival appears less typical and more exceptional. Astronomers have discovered countless exoplanets orbiting other stars. Many reside at distances where sunlight should allow liquid water. From afar, these worlds appear promising. Their orbits fall within regions often called habitable zones, where temperatures could permit oceans, yet habitability is not guaranteed by distance alone. Some of these planets are frozen despite receiving sufficient light. Thick ice covers their surfaces, reflecting starlight back into space. Once ice establishes dominance, warming becomes difficult. These planets enter states where oceans, if they exist at all, lie buried beneath kilometers of frozen shell. Heat from the interior may keep water liquid below, but the surface remains locked in cold. Other worlds experience ice lock through orbital quirks. Planets that rotate slowly or are tidally locked, always showing the same face to their star, develop extreme temperature contrasts. One side bakes under constant light while the other remains in permanent darkness. Ice accumulates on the cold side, spreading outward. As it grows, it reflects more light, cooling even the illuminated regions. Over time, the entire planet can slip into global freeze. In these cases, recovery is rare. Without active geology to replenish greenhouse gases, atmospheres thin. Without oceans exposed to air, heat exchange slows. The planet settles into a stable frozen state, not because it lacks energy entirely, but because it cannot redistribute or retain it effectively. These outcomes reveal why habitable zones are misleading when taken alone. They describe where liquid water could exist, not where it will persist. A planet may sit comfortably within this zone and still freeze permanently if other conditions fail to align. Atmosphere, internal heat, rotation, and surface feedbacks all matter deeply. Many worlds lack sustained volcanic activity. Their interiors cool early, shutting down carbon recycling without continuous replenishment. Atmospheric gases escape or are locked away. Ice spreads. Reflection dominates. The planet crosses thresholds that are difficult to reverse. Others lose their atmospheres to stellar winds. Without magnetic protection or sufficient gravity, gases are stripped away over time. Even a planet with abundant water can become cold and airless, its oceans freezing or evaporating before settling into stillness. Some planets never develop deep oceans. Shallow water stores less heat and freezes more readily. Without depth, there is little thermal inertia to resist rapid cooling. Ice advances quickly, and recovery requires dramatic changes that may never arrive. When these factors combine unfavorably, the result is a world that appears quiet and unchanging. Ice persists, climate stabilizes in cold, the planet becomes predictable but lifeless at the surface. Seen against this backdrop, Earth appears unusual, not because it avoids freezing entirely, but because it repeatedly approached that fate and turned away. It retained its atmosphere. Its interior stayed warm. Its oceans remained deep and active. Its feedbacks aligned often enough to preserve motion. This does not make Earth perfect or secure. It makes Earth rare. Many planets may flirt with habitability briefly, only to lose it. Long-term stability requires persistence across many systems, each vulnerable to failure. Earth's story suggests that survivable climates are not the default outcome. They are contingent results of overlapping advantages. Remove one, and the balance shifts. Delay one, and thresholds may be crossed. In this sense, Earth is an outlier, not a template. It demonstrates what is possible, not what is typical. Its long history of near failure underscores how easily a planet can slip into permanence, whether hot or cold. The frozen exoplanets scattered across the galaxy are not anomalies. They are expressions of planetary physics playing out without interruption. Ice lock is not an accident. It is a common outcome when stabilizing processes weaken or misalign. Earth's continued warmth, its open oceans and dynamic surface reflect a convergence of factors that did not have to occur together. That they did is not a guarantee for others. In the quiet observation of distant worlds, Earth's survival reads less like inevitability and more like exception. A planet that remained active long enough, stable enough, and lucky enough to avoid the stillness that claimed so many others. As Earth continues its long journey, the forces that once held it close to ice have not vanished. They have only slowed, stretched across spans of time so vast they resist ordinary imagination. The question of whether Earth could ever freeze forever does not belong to tomorrow or even the distant future of civilizations. It belongs to deep time, where change unfolds patiently and without urgency. One of the quiet trends shaping that future is cooling from within. Earth's internal heat, inherited from formation and sustained by radioactive elements, leaks away slowly. This heat drives plate motion, volcanism, and the recycling of carbon between rock and air. Over immense spans, that reservoir diminishes. The planet does not cool abruptly. It cools by degrees so small they are invisible within a lifetime, yet decisive across hundreds of millions of years. As internal heat fades, volcanic activity declines. Eruptions become less frequent. The steady release of carbon dioxide from the interior weakens. With less carbon entering the atmosphere, the long balance between warming and cooling shifts. Weathering continues to remove carbon, but replacement slows. The sky thins gradually. Heat escapes a little more easily. This process has already begun. Earth today is less volcanically active than it once was. Plate motion persists, but it is not eternal. The planet's engine will one day idle, then slow further until motion becomes rare. When that happens, one of Earth's most important climate stabilizers will weaken. At the same time, the sun continues to change. Unlike Earth's interior, the sun grows brighter as it ages. Nuclear reactions at its core become more efficient, increasing the energy Earth receives. This brightening acts against cooling, pushing the planet toward warmth rather than ice. For a long while, these trends oppose one another. Declining volcanism reduces greenhouse gases, increasing sunlight adds heat. The balance between them shifts slowly, redefining what stability means. In the nearer future, the sun's brightening is expected to dominate, making permanent freeze unlikely. Yet this balance does not remain simple forever. As the sun ages further, its changes become more dramatic. Over extremely long spans, its output will alter Earth's climate in ways that do not favor ice, but also do not favor life as it exists now. Before freezing becomes a concern again, other extremes arrive. Still, beyond those eras, when the sun's life nears its end, cooling could return. The planet's interior would be largely quiet by then. Volcanic carbon release would be minimal. Plate tectonics might cease. Weathering would draw down what little greenhouse gas remained. The sky would thin. Oceans could cool. Ice could spread. These scenarios unfold on timescales that dwarf humanity. Hundreds of millions of years pass like moments. Entire species rise and vanish. Continents rearrange. Oceans open and close. Against this backdrop, the possibility of permanent freeze exists not as a looming threat, but as a distant chapter written far ahead. Whether Earth could freeze forever again depends on alignment, just as it always has. If internal heat fades before solar brightening overwhelms cooling, ice could gain ground. If the atmosphere thins too much, recovery becomes harder. If oceans lose circulation, heat storage weakens. But the timing matters. The sun's evolution is not gentle forever. Its later stages do not favor ice lock in the way a faint young sun once did. The conditions that allowed near-permanent freeze earlier in Earth's history may never return in the same form. What remains certain is that Earth is not fixed. It does not settle into a final state and remain there indefinitely. Its climate continues to drift, guided by forces operating on different clocks. Some tick slowly, others race ahead. Their interactions shape outcomes that are never guaranteed. The idea of Earth freezing forever again is not a warning for our time. It is a reminder of scale. The planet's stability exists within a window bounded on both sides by extremes. That window moves as stars age and interiors cool. Human history occupies a thin slice within this vast continuum. The changes that decide planetary fate unfold far beyond it. From this perspective, permanence itself becomes an illusion. Ice ages come and go. Warm periods rise and fade. Stability lasts only as long as the forces supporting it remain aligned. Earth's future, like its past, will be written slowly. Whether it ends in ice, heat, or something unfamiliar depends on sequences that stretch beyond imagination. What can be said is simple and quiet. The planet has frozen before, nearly permanently. It could approach such a state again, but only in a future measured not in years, but in the deep, patient language of time itself. Across Earth's long history, liquid water has never been far from vanishing. Oceans appear vast and enduring, yet their existence depends on a narrow range of conditions that must be continuously maintained. Temperature, pressure, atmospheric composition, and circulation all contribute to whether water remains fluid or slips into ice. Remove or weaken any of these influences, and the balance shifts. Liquid water survives on Earth because warmth arrives at the surface just fast enough and escapes just slowly enough. Sunlight provides energy, while the atmosphere and oceans decide how long that energy stays. When either side of this exchange changes, water responds quickly. A slight cooling allows ice to form. Once ice appears, it reflects light, reducing absorbed heat and encouraging more freezing. The transition from open ocean to ice-covered surface can begin with only a modest nudge. This closeness is not limited to polar regions. Even in warmer eras, much of Earth's water exists near freezing temperatures. Deep oceans remain cold, storing heat but never far from solidification. Surface waters circulate constantly, carrying warmth toward colder latitudes where it is lost. The entire system operates near thresholds, relying on motion and exchange to remain liquid. Because of this, Earth never becomes fully safe from freeze. There is no permanent buffer that guarantees liquid oceans regardless of circumstance. Stability arises from activity, not from distance to danger. As long as heat moves, gases cycle, and interiors remain warm, water persists. When any of these slow or stop, ice gains ground. Climate, then, is not a fixed setting. It is a moving balance, adjusting continuously to forces that change at different speeds. Some shifts occur over days or seasons, others unfold across millions of years. The balance is dynamic, responding to both internal rhythms and external influences. This movement prevents the planet from settling into permanent safety. Each moment of stability is temporary, held in place by alignment rather than by certainty. Earth remains habitable not because it has reached a secure state, but because opposing processes remain active and engaged. Ice ages illustrate this clearly. Even when oceans remain open globally, ice advances and retreats repeatedly. The line between liquid and solid migrates across the surface, advancing during cooler periods and retreating during warmer ones. The planet oscillates, never fully locking into ice, yet never far from doing so. These oscillations are reminders that climate does not seek equilibrium in the way simple systems do. It responds to feedbacks that can strengthen or weaken depending on context. When stabilizing forces dominate, change slows. When amplifying forces gain influence, change accelerates. The balance point itself moves. Stability, in this sense, becomes an illusion. What appears steady on human timescales often masks gradual drift. Oceans may remain liquid for millions of years, yet underlying conditions may be shifting quietly. Atmospheric composition changes, continents rearrange, internal heat wanes. Each adjustment alters how close water sits to its freezing point. The illusion deepens because life adapts to prevailing conditions. Ecosystems flourish, giving the impression of permanence. Yet life responds to climate. It does not anchor it. When physical conditions shift far enough, adaptation gives way to retreat. Earth's history shows that liquid water has survived not by resting comfortably within wide margins, but by navigating narrow corridors. The planet repeatedly approached ice-dominated states, then recovered through slow accumulation of heat and gases. Each recovery required time and favorable sequencing. This fragility does not imply instability at every moment. It implies vigilance built into the system itself. The planet remains active, restless, and responsive. Oceans circulate, plates move, volcanoes breathe. These motions keep the line between ocean and ice from settling in one place for too long. Yet none of these processes are guaranteed to persist forever. Their continuation depends on internal energy and external context. As those change, the line shifts again. Understanding this thin line reframes Earth's story. Habitability is not a destination reached and secured. It is a condition maintained through motion and balance. The oceans exist because the planet never stopped adjusting. In the quiet perspective of deep time, water appears less like a permanent feature and more like a temporary state, preserved through constant negotiation. Earth never becomes safe from ice. It remains liquid only by continuing to move, change, and respond, holding the line not through certainty, but through ongoing balance that must be renewed again and again. As Earth's long journey comes into clearer view, one truth settles quietly beneath every chapter. Survival was never promised. The planet did not follow a guaranteed path toward warmth, oceans, or life. It moved through a system governed by physical laws that allow many outcomes, most of them indifferent to habitability. Planetary systems offer no assurances. They begin with similar materials and energies, yet diverge quickly. Small differences at birth grow larger with time. A little more mass, a little less heat, a slightly altered orbit, and the future changes. Physics provides rules, not protections. Within those rules, outcomes vary widely. Earth formed in a region where liquid water could exist, but that position alone meant little. Other planets share similar locations and still froze or dried. Distance from a star sets a possibility, not a promise. Everything else depends on how the planet evolves afterward. Luck enters not as randomness without cause, but as sensitivity to timing. Physical processes unfold on different clocks. Some act quickly, others require millions of years. When these clocks align favorably, stability emerges. When they do not, collapse follows. The alignment itself is not guided. It happens or it does not. Earth benefited from fortunate sequencing again and again. Internal heat lasted long enough to drive tectonics. Volcanic activity continued when ice threatened. Oceans formed deeply enough to store heat. The atmosphere remained thick enough to trap warmth. None of these factors were guaranteed to persist together. If any one of them had faded earlier, the outcome could have changed. A quieter interior would have reduced carbon recycling. A thinner atmosphere would have leaked heat. Shallower oceans would have frozen more easily. Each margin was narrow. In this sense, Earth should be understood as a survivor rather than a certainty. Its present condition reflects a history of close calls rather than a smooth ascent. The planet endured because it avoided failure repeatedly, not because failure was unlikely. Survivorship bias can make Earth seem typical. We observe it because it endured. Frozen worlds and failed climates remain silent. Yet when viewed alongside them, Earth's long habitability stands out as uncommon. The laws of physics do not prefer life. They allow it under certain conditions, but they do not protect it. Ice forms readily, heat escapes easily, atmospheres thin, feedbacks amplify extremes. Stability requires effort, motion, and time. Earth's margins were narrow from the beginning. It balanced between a faint sun and a reflective surface. It balanced between greenhouse warmth and chemical removal. It balanced between internal heat and surface cooling. Each balance could have tipped. Even after life appeared, survival remained uncertain. Biology influenced climate, but it could not override physical thresholds. Life adapted repeatedly, retreating into refuges when conditions worsened. Had extremes deepened slightly more, adaptation would not have been enough. The story that emerges is not one of destiny, but of persistence under constraint. Earth remained habitable because stabilizing processes continued just long enough, often by coincidence of timing rather than strength. Luck, in this context, does not mean chance without structure. It means outcomes shaped by complex interactions where small differences matter. When volcanic gases accumulated during ice cover rather than before, it mattered. When continents moved into positions that enhanced weathering at the right times, it mattered. When oceans circulated heat during vulnerable periods, it mattered. These events did not aim toward survival, they followed physical rules. Survival emerged as a byproduct. This framing changes how Earth's history is understood. The planet did not march confidently toward a stable future. It wandered close to edges, corrected course, then wandered again. Its climate history is marked by recoveries that were never assured. Earth's survival was not inevitable because the system allowed many endings. Permanent freeze was one, permanent heat was another, atmospheric loss was possible. Ice lock waited nearby more than once. What prevented these endings was not a single safeguard, but a chain of near successes. Each one depended on conditions that could have failed independently. The chain held, not because it was strong, but because it was never pulled apart all at once. In the quiet language of deep time, Earth's story becomes one of narrow margins, a world that stayed alive not by certainty, but by threading a path through possibility. A survivor shaped by physics, timing, and chance alignment, reminding us that existence itself is often less guaranteed than it appears. As Earth's story settles into its larger meaning, it naturally reaches outward. The narrow margins that shape this planet do not belong to Earth alone. They frame how life might emerge, struggle, and endure elsewhere in the universe. Many planets may briefly appear habitable. They may host liquid water for a time, maintain a suitable atmosphere, and orbit within gentle ranges of stellar light. These conditions are enough to spark interest, but they are rarely enough to last. Habitability is not a moment, it is a commitment measured across billions of years. The reasons many habitable planets fail are often subtle. Some lose their atmospheres slowly, stripped away by stellar winds or weakened gravity. Others cool internally, shutting down volcanism and carbon recycling. Some become locked into ice through feedbacks that overpower stabilizing processes. None of these failures require catastrophe. They unfold gradually, often invisibly. Short-term habitability is common in planetary systems. Long-term stability is not. To endure, a planet must continuously adjust to changing conditions. Stars brighten, interiors cool, orbits shift. Each change introduces new stress. Without mechanisms to respond, a planet drifts toward extremes. Earth survived because it possessed multiple overlapping systems that remained active for a very long time. Its atmosphere stayed thick, its interior stayed warm, its oceans stayed deep, its surface remained dynamic. These factors did not merely exist, they persisted together. This persistence may be rare. Many planets form with one or two favorable traits, but few maintain all of them across deep time. A planet might have water, but lack tectonics. It might have an atmosphere, but lose its magnetic field. It might start warm, but cool too quickly. Life requires more than water. It requires time. Time for chemistry to organize, time for adaptation to respond to stress, time for recovery after disruption. Without long stretches of relative stability, life struggles to move beyond simplicity. Even microbial life, resilient as it is, depends on conditions remaining within certain bounds. Freeze the oceans completely, and chemistry slows. Strip the atmosphere and radiation penetrates. Heat the planet excessively, and water escapes. Life survives only where physical systems allow it to persist. Earth provided this allowance repeatedly, not by remaining unchanged, but by changing slowly enough. Climate shifted, but not too fast. Ice advanced, but not irreversibly. Heat returned, before thresholds were crossed. This pacing mattered as much as the conditions themselves. Survival over billions of years demands more than favorable beginnings. It demands resilience against cumulative change. It requires a planet to withstand its star's evolution, its own internal cooling, and the random alignments of orbital dynamics. This perspective reframes the search for life elsewhere. Discovering water or a suitable orbit identifies possibility, not durability. The deeper question becomes whether a planet can remain active long enough for life to gain a foothold and endure repeated challenges. Earth's history suggests that such endurance is uncommon. The universe may host countless worlds that flirt with habitability only to lose it. Life may arise often, but survive rarely. This does not diminish the universe, it deepens it. Each surviving world becomes more remarkable, not because it was destined, but because it navigated constraints successfully. Each long-lived biosphere represents a path that avoided many endings. Earth stands as one example of this outcome. It does not define the norm. It reveals the difficulty. Its survival reflects a chain of conditions that remained aligned just long enough over and over again. For life elsewhere, this means that discovery may favor youth. Young planets around quiet stars might host life briefly. Older systems that retain habitability may be fewer. The universe may be rich in beginnings and poor in continuations. Yet even this scarcity does not imply emptiness. It implies value. Long-lived worlds, when they exist, carry histories shaped by resilience rather than guarantee. Earth's story offers a lens, not a template. It shows that life requires patience from its planet, protection from extremes, and time beyond measure. It shows that survival is earned through balance, not bestowed by location. In this light, life elsewhere becomes not just a question of where, but of how long. The quiet answer carried by Earth's deep past is simple. Endurance matters more than origin, and worlds that manage it are likely rare, precious, and shaped by the same narrow margins that once kept our own oceans from freezing into silence. Beneath our feet, the ordinary feels permanent: warm ground, flowing water, air that moves gently between seasons. These conditions fade into the background of daily life, so constant that they seem inevitable. Yet in the long view of Earth's history, none of this was guaranteed. What feels stable is the result of countless narrow escapes, layered one atop another, preserved through balance rather than certainty. Everyday warmth is not the default state of a rocky planet. It is an outcome shaped by alignment. Heat arrives from the sun and from within the earth, then lingers just long enough to matter. It is slowed by the atmosphere, shared by oceans, recycled through rock, and moderated by motion. Remove any one of these influences, and the warmth we experience would thin or vanish. The ground beneath us holds memory of this fragility. Stone remembers times when ice lay close to the equator. Sediment remembers oceans sealed beneath frozen skies. The warmth we now feel is not a steady inheritance. It is a temporary balance struck between opposing forces that have never stopped pulling. The existence of oceans themselves borders on improbable. Liquid water requires a precise combination of pressure and temperature. Too cold, and it freezes into reflective silence. Too warm, and it evaporates, escaping slowly into space. Earth has remained between these states not by resting comfortably, but by continually adjusting. Oceans persist because heat moves. Sunlight warms surface waters. Currents carry that warmth away. Depth stores it. Atmosphere exchanges it. This motion keeps water fluid. When motion slows, ice advances. When exchange weakens, extremes sharpen. There were moments when oceans nearly vanished from the surface, hidden beneath ice thick enough to shut down interaction with the sky. Recovery depended on heat that had not yet escaped, on gases that continued to build, on motion that never fully ceased. That recovery was possible does not make it likely. It makes it rare. Earth remains close to extremes even now. The difference between open water and widespread ice is smaller than it appears. Shifts measured over long spans, changes in gases or sunlight or circulation, can redraw the boundary. The planet does not drift far from this edge, it lives alongside it. This closeness is not a flaw. It is the condition under which balance operates. Earth's climate does not settle into safety. It oscillates, corrects, and responds. Stability emerges from activity, not from distance to danger. The warmth that allows forests, rivers, and oceans exists because opposing processes remain engaged. Cooling and warming never stop. They counter one another continuously. When one gains advantage, the other responds, slowly, imperfectly, but often in time. This makes Earth balanced, not secure. Balance implies effort. It requires ongoing adjustment. It can be lost if forces drift out of alignment. Security would imply permanence, and permanence does not exist at planetary scales. What makes this a quiet miracle is not that Earth avoided catastrophe once, but that it avoided it repeatedly. Each era carried new risks. Internal heat declined, the sun brightened, continents moved, life altered the atmosphere, ice advanced and retreated. Through all of this, the planet remained liquid often enough for life to persist. None of these outcomes were scripted. They depended on processes that happened to continue when needed. Volcanic gases accumulated when ice sealed oceans. Plate motion exposed fresh rock when carbon needed removal. Oceans circulated heat during vulnerable periods. Timing mattered as much as presence. Standing on warm ground today means standing on a history of narrow margins. The warmth beneath our feet is the residue of successful alignment across billions of years. It feels solid, but it rests on motion and balance that could have failed. Earth has never been far from becoming something else. A frozen world, a dry one, a silent one. That it is not those things reflects a path taken through possibility, not a destination guaranteed. The miracle is quiet because it does not announce itself. It hums beneath stone, flows through water, drifts through air. It is present in the ordinary, in the unremarkable warmth of a day that feels like it has always been this way. But it has not, and it will not always be. For now, Earth remains balanced. Oceans breathe, heat moves, ice waits at the edges. The planet holds itself between extremes, not secure but sustained. A world that survives not by certainty, but by continuous, delicate adjustment, renewed moment by moment across deep time. Earth's story does not end with triumph. It settles instead into perspective. When viewed across deep time, this planet reads less like a tale of certainty and more like a record of near misses, each one quietly avoided, each one capable of ending everything that followed. From its earliest moments, Earth stood close to failure. Heat could have escaped too quickly, ice could have spread too far, the atmosphere could have thinned beyond recovery. Oceans could have vanished beneath reflective silence. None of these outcomes would have violated the laws of physics. They would have fulfilled them. What allowed Earth to last was not immunity, but balance that held just long enough. Forces that warmed the planet persisted. When cooling threatened to dominate, Processes that cooled the planet responded when warmth grew excessive. The timing of these responses mattered as much as their strength. Survival emerged not from protection, but from alignment. This makes Earth a near miss story at every scale. At the scale of stars, it orbited a sun that was once too weak, then slowly too strong. At the scale of geology, it retained internal heat long enough to keep moving. At the scale of climate, it hovered near thresholds without crossing them fully. At the scale of life, it endured stress after stress without slipping into permanence. Nothing in this sequence was guaranteed. The planet did not follow a protected path. It navigated a narrow corridor shaped by physics, chance alignment, and persistence. Many worlds likely entered similar corridors and never emerged. Their surfaces froze, their atmospheres faded, their stories ended quietly. Earth survived without guarantees. That truth deepens rather than diminishes its wonder. The oceans exist not because they had to, but because conditions allowed them to continue. Warmth persists not because it is stable forever, but because opposing forces still engage one another. Life thrives not because the planet promised safety, but because safety lasted long enough. This understanding reframes how stability is perceived. Stability is not a destination Earth reached, it is an ongoing process, maintained through motion and response. The planet remains active beneath our feet, recycling rock, circulating water, adjusting its atmosphere. These motions are not signs of unrest, they are the reason the surface remains alive. Planetary fragility does not imply weakness, it implies sensitivity. Earth responds to change because it must. When conditions drift, feedbacks answer. Sometimes they succeed, sometimes they barely do. The record shows that Earth often came close to losing this balance, and that recovery required patience measured in millions of years. This fragility extends beyond Earth. It suggests that long-lived habitable worlds are not the default outcome of planet formation. They are achievements shaped by timing, persistence, and overlap of many processes. The universe may be filled with beginnings that never matured, climates that stabilized briefly and then failed. Seen this way, Earth becomes less ordinary and more instructive, not because it is unique in principle, but because it demonstrates how demanding long-term survival truly is. It shows that life does not require perfection, but it does require time, motion, and a planet willing to keep adjusting. These closing thoughts do not seal the story. They soften it. They invite reflection rather than conclusion. Earth's past does not point towards certainty about its future. It reminds us that outcomes remain contingent, shaped by forces still unfolding. The ground beneath us carries this memory quietly. Stone remembers ice, oceans remember warmth, the atmosphere remembers balance. None of these memories promise permanence. They tell us instead that survival has always been provisional. To understand Earth fully is not to seek comfort in its endurance, but to appreciate the fine margins that made that endurance possible. The planet almost did not last. That it did is not a resolution, it is an opening. There are more stories hidden in deep time, other moments when Earth nearly failed, other worlds that did, other thresholds waiting to be understood. Exploring them does not diminish the present, it deepens it. If this journey through Earth's narrow survival has stirred quiet curiosity, there are countless other chapters written in stone, ice, and ancient oceans. They wait patiently, not to alarm or reassure, but to remind us how delicate and remarkable planetary stories truly are.